Are we live or not yet? Yeah, let me know when it's live then. I don't know why it's not live.
It is live now.
Oh, it's live now? Okay. Okay, that's good. For some reason, there's this delay. That's the importance of low latency, I guess, right? You cannot go live right away. Okay, let's get started. Today, we're going to continue what we started last time, memory controllers. This is such an important topic, but I will try to restrict it to this lecture because we have a lot of other things to cover as well. Tomorrow, I intend to cover the emerging memory technologies that I promised for some time, which is also controlled by memory controllers. So memory controllers are actually quite important to know how memory is in general managed. Right? So today, we're going to look at different aspects of memory controllers, especially focusing on service quality or quality of service, predictability if we have time. And of course, we'll always talk about performance, right? Since performance is important. But to jog your memory, yeah, this is what we were talking about. And I'm going to go through some slides we covered last time so that I get to some point. And then we're going to talk about resource sharing and its advantages and disadvantages. But recall the slide we were talking about DRAM controllers. We were discussing why DRAM controllers are difficult to design. And we were discussing why this problem is going to be even more important into the future because you have heterogeneous agents injecting requests into the memory controller and heterogeneous memories, as we will talk about, especially tomorrow. And memory control is going to be more important so that you can satisfy the requirements of different agents while taking into account characteristics of different memories. And there are many, many requirements, different types of requirements in the applications that are executing over here. And there are different kinds of memories which have different characteristics. And matching all of those together is not an easy task, as we discussed. In fact, even performance is not an easy task by itself, right? How do you actually come up with a policy that maximizes system performance under many workloads and many different conditions? This is, even we don't know how to do this at this point. That's why we talked about this, let's say, dream that we had a while ago. Can we design a DRAM controller that automatically found a good scheduling policy on its own, given all of these timing constraints, given different applications that are generating requests, and yeah, so on, basically. And this is just about performance, if you remember. Extending this for quality of service, energy, predictable performance, etc., is still a very interesting research area, in my opinion. How do you actually design a machine learning policy that can do this automatically with as little input as possible from humans is important, I think. And recall, we were talking about self-optimizing memory controllers. I'm not going to go through this again, but we used reinforcement learning to do the memory scheduling so that hopefully the DRAM scheduler over time figures out a better policy so that it can maximize its long-term rewards whenever it takes an action in a given state, which is essentially the fundamentals of reinforcement learning. And if you want to know about, more about reinforcement learning, I recommend Richard Sutton and Andrew Bartow's book on reinforcement learning. You can find online. The PDF is all available free. And that's actually perhaps the best introduction to reinforcement learning. And it has a recent edition, actually, in 2018. And it uses our work as an example of a good application of reinforcement learning. It talks about AlphaGo, for example. And it also talks about this work as some applications of reinforcement learning that can have a lot of potential. So it's good to see the applications in that, but also it's good to see the theory. Okay, yeah, but any reinforcement, whenever you design some reinforcement learning policy, you have to specify rewards, state attributes, and actions. And we discussed that this needs to be done by the designer. Now the designer burden shifts to something else, right? As opposed to dictating the policy, they have to describe these three major things. And some of them may be easier, some of them may be harder. As we discussed, reward can be hard depending on what your goals are. States can be potentially automated. Actions are usually the easier thing to do. And we said that you gain large, robust performance improvements. And this is going to be one of the papers that you can read and review if you want. And that's the paper. And then we said that perhaps this is a good way of designing computing architectures in general, right? If you look at architectures today, you have policies all over the place that are all human-driven, right? There are very few, maybe you can actually count with 3 fingers or maybe 2 fingers how many policies that are actually machine learning driven or data driven today. as opposed to human-driven. And as a result, we have very simple, short-sighted policies that cannot adapt to different workloads easily because we cannot learn the policies automatically, right? And there's almost no learning, basically. This is very different from a human that, as we discussed, we philosophized a bit. Then the question is, can we design fundamentally intelligent architectures that can learn from the past, basically? And that's an example. The self-optimizing memory control is just an example of this, right? In my opinion, there's a very rich area to explore actually going into the future, which is not explored as much. There's a lot of exploration on how to accelerate machine learning, which is good and interesting. And we need to broaden the scope of it also to many, many machine learning algorithms. But there's less exploration. It's increasing, but there's less exploration on how do we actually rethink the design of all of our controllers, hardware, as well as software, such that they're fundamentally better and fundamentally more intelligent. And I think this is a very rich area because there are many controllers in our systems. They make individual decisions. They need to coordinate also with each other sometimes. And they're all human designed, right, if you think about it. And humans are good at simple things, getting insight. But if your state space is huge, humans are terrible at dealing with very large state spaces, right? And also complex equations, right? For example, it's very hard for a human to decide what is going to be the long-term impact of a scheduling decision that you make at this point. And what's going to be the impact 100,000 cycles later, right? Because you don't know what's going to come, right? But if you learn somehow based on past behavior, collected a lot of information, data, that's what data-driven means basically, then you can actually have a chance to adapt your policy. But a human designer sitting in front of their computer, designing this memory controller, they don't have access to this, right? And they also, in my opinion, at least they don't know how to use their capacity, brain capacity to enable something like this. Okay. And we discussed that there's other work that we are doing in this area, and Rahul is going to present that next week. So next week, I intend to have some research presentations that I promised to you in the past. So we will have hopefully a lot of interesting cutting edge research presentations on different topics, especially the topics we have covered. And Rahul is going to cover this reinforcement learning based memory prefetches. Okay, and then I mentioned that maybe fundamentally better architectures are all data-centric, data-driven, and data-aware. I mean, we've covered the data-centric architectures clearly in the past lectures. Data-driven, I've given you examples of. Data-aware, we also discussed, right? For example, whenever we discussed the latency management to improve energy efficiency and performance of deep neural networks, you look at the characteristics of different types of data in terms of how much error they can tolerate. And based on the errors they can tolerate, you change the latency and voltage of different portions of DRAM so that you can match the error tolerance or tolerable bit error rate. So that's an example of a data-aware policy. And I think going forward, we need similar policies that can take advantage of characteristics of different data so that you can optimize the system. So maybe we'll cover more examples of this data-aware, actually. I don't know if I have slides. I think I removed the slides since we don't have time to go over them right now, but we may have another lecture related to this. Okay, so I think this was a slide that I rushed over, but I think we've covered a lot of these. Basically, we covered the processor-centric versus data-centric difference. We covered the human-driven decisions versus data-driven. And we covered kind of component-aware decisions versus data-aware decisions because we don't have the characteristics of data. Usually, the controllers we design make component-aware decisions. For example, I'll pick one example from memory controllers, right, again. If you look at a memory controller, the decisions are made based on the state of DRAM, state of the scheduling queue, and the requests, right? You don't consider what data is being accessed. And that's what I mean by component aware. It's all about the component that you're designing. But maybe what's important is really how important is the reliability of the data you're accessing, right? We discussed this. And your policy changes based on the reliability characteristics or error tolerant characteristics of the data. Or how important is it to get this data first from a criticality point of view for the application, right? How critical is this data for the progress of the application or for user to be satisfied, let's say. Maybe that's one data is much more critical for the user, right? But that information is not present at all in the memory controller or cache. Pick any component that we're looking at in this course. That information doesn't get communicated to the architecture, right? We don't know which data is more important or less important. We basically just, everything is the same. But that's not true in real life, right? At the high level, semantic level, from a user perspective or programmer perspective, some data, different data have different characteristics, right? Some of them are more important for performance. Some of them are security critical. Some of them, I don't care about the security, right? Some of them have to be absolutely correct when you access them, but some of them you can tolerate some errors in them, right? So there are many, many different characteristics of data that doesn't get communicated. As a result, I think our controllers or system design in general is missing this rich semantic information that doesn't get communicated. And building a data-aware architecture, in my opinion, is just all about communicating, or first of all, finding out that information, what are the different characteristics of data, communicating it to the hardware and the software, such that the underlying architecture can make much better decisions. Perhaps prioritize the more critical data, for example, right? Again, there are many dimensions, right? A user may know about the compressibility of the data, how much lossy compression you can tolerate, for example. That could enable you to manage your memory in a much better way, right? They may know about the privacy characteristics of the data. This data has to be private, so don't leak any information. Maybe you can turn off privacy or security mechanisms on that data, right? It's not important to the user. They clearly specify it, assuming they know what they're doing, of course. But some data may be extremely private, and you should really protect it in some place. And maybe you access it slowly because it's so important for privacy. Right? So I think this sort of semantic information is missing in general in system design. And perhaps this is the less explored area in these three things: data-centric, data-driven, and data-aware. And I think going forward, we need to explore it more, in my opinion. Of course, to communicate this information, you need to have better interfaces across the stack, right? If you look at the hardware-software interface, we're dealing with instructions, right? And we're not able to encode much characteristics of the data, right? That encoding doesn't exist today between the hardware and software interface. Sometimes we're not even thinking about it, so encoding may be secondary also, but we still need to communicate it somehow. Okay, so this is what I mentioned. I think this is kind of where we left off, actually. We were kind of philosophizing about the brain, and I think this is much more data-centric, data-driven, and data-aware compared to the computing systems that we're building today. So the computing systems that we're building today are actually, if you think about it, we may be violating all the principles that this thing is based on. I think we're learning a bit more on the heterogeneity side, right? I think systems are becoming much more heterogeneous today, and this is clearly very heterogeneous. Its components are specialized. It has components that are extremely specialized for vision, for example, faces, the language, etc. And we're kind of getting there maybe in the computing system design, but maybe that's the only principle that we're exploiting here, right? This is definitely not processor-centric based on all we know about it, right? It's very much data and memory and storage, memory and computation combined. Anyway, we can talk more about it, and this is probably a different course that requires some neuroscience background also, but we don't have time. But I think it's good to think about this basically. In a sense, we're thinking about intelligence, right? And we're talking about artificial intelligence all the time. And we're saying, oh, these computers are intelligent. But at a fundamental level, they're stupid, right? They have no intelligence. The characteristics that we assign to humans as being intelligent, computers are not good at it. They may be very good number crunchers still. And I think if you look at the core of the neural networks, I'm taking aside maybe reinforcement learning, that's a bit different, I think. But if you look at the core of neural networks, it's also number crunching. It's a bit difficult to believe that this is just number crunching at its core, but people show that there are different processes, of course, but it's not just number crunching, basically. And this is actually not extremely good at number crunching. It's very slow at number crunching, if you will. Okay, but that's a bit more philosophy, and it requires a lot more depth to go and to be more scientific about it. But I think it's good to think about this. So maybe we need better systems to call them intelligent, right? Okay, I think all of these require rethinking the stack, as we discussed a lot of times in this course. This is a paper that I wrote actually about this topic that's specifically covering these three, like a blueprint for fundamentally better architectures. It's of course a very short paper. It's a position paper that talks about basically this data-centric, data-driven, and data-aware paradigm. If you're interested, you can read it. It's very short. It's only 4 pages or so. And we've covered a lot of this that I delivered in the tutorial. Okay, any questions? That's kind of a long ending to the basic memory controller part. Now we're going to look into more issues in memory controllers. And in general, systems with shared resources. Okay, yes, there's one. Please press the button so that people can hear.
So why have the as compared to more data-centric view? I mean, the market clearly needs these solutions. So
I didn't get the first part. Why has what?
So why did the manufacturers, for example, CPU manufacturers or memory manufacturers, always focus on performance as compared to a more data-centric approach? Because clearly the market today needs it, right? You have these different enterprise vendors and you have these different end consumer vendors, and everyone has very different characteristics, and yet everyone gets sold the same XYZ commodity component. I don't know.
Well, maybe I'll rephrase your question a little bit, because it's not just about, it's not performance versus data centric, right? You can achieve performance with the existing design paradigms also, and the goal is to achieve high performance, of course. And I think going data centric clearly, as we've seen in this lecture, in this course, buys you a lot more performance. The reason the way we're doing the systems today is because that's how it's been like that, right? It's, in a sense, it's precedent-based design. In the past, it's been like that. And we're kind of in this business as usual model, right? It's always difficult to break business as usual models, I think. You have to come up with a disruptive approach. And I think what I showed you earlier is disruptive in a sense, but it takes time to disrupt business as usual. So I think it's happening again, step-by-step processing. What was that up? Step-by-step processing in memory or data-centric or data-driven approaches will come. It requires a lot of research and development and efforts. No question about that, right? Does that make sense?
Yeah, thank you.
Sure. Yes.
Regarding that question, I have a possible answer.
Okay.
Maybe the architecture nowadays are more like general purpose, but data-centric architecture are more focused on typical tasks. Is it right?
More focused on what?
Typical tasks.
Okay.
I wonder if this is right.
Well, I think, I mean, data-centric architectures can also be general purpose, right? What we have seen in the processing using and processing near memory lectures. But certainly, current architecture is more general purpose. As they become more specialized, I think that's where we can also integrate better some of these disruptive approaches. I agree with that, I think. So as specialization becomes more important, you will also think about, okay, let's specialize the system such that you become more data-centric, where absolutely a processor-centric approach doesn't work very well. Yeah, but I think, yeah, it's in the end, even there, it will be difficult to disrupt. But it requires more research and education for sure, and more, let's say, boldness. Okay, yes.
So earlier you mentioned that one thing that people struggle with would be seeing how, I guess, long-term decision making. So how something made this clock cycle will affect something 100,000 ones later. And so I guess I'm curious about the order of magnitude, I guess, of these kinds of things. How close, I guess. So it's a huge state space in which it's really difficult to optimize. But just the human heuristically driven solution, is that within 95% of the optimal? So I guess the question is for a component level, just for the component level. So maximizing the throughput of the memory controller, has there been work to calculate the ideal and then compare that to what's achieved by the common human driven memory scheduling?
Yeah, there has been work. I mean, our paper has some of that, and I would encourage you to read it. There is definitely a lot of headroom compared to human design heuristics. And yes, of course, it depends on different components, right? Different components have different headroom in the end, if you look at just performance. But then there are energy aspects of it also. So it's very hard to quantify everything, right, in terms of what's ideal, because there are multiple metrics you're optimizing for. But there is headroom. People have shown that there is headroom in caching, especially in caching, for example. If you look at the efficiency of caches we have today, they're not very efficient. Most of the data inside your huge cache is not used, is not going to be used. So maybe there's a better management policy. So the headroom is there, but this doesn't mean that we have found the management policies, like learning policies, to figure out what needs to go there, right? And that's part of research, I think, because we haven't done enough research. So we've done a lot of research on heuristics, for example, the caching. Caching was invented in 1962, around that time, basically. And we're 50, how many years? 60 years ago, right? And there have been a lot of papers, heuristic-based methods on caching, but there are only a handful of papers on using machine learning for caching that are appearing just now. So over time, I think those papers, those works will show the value better, right? And also the headroom, that's a very good question because now it goes to evaluation, right? Remember the picture that I showed you from the book System Performance Analysis, where the author showed, okay, these are many reasons to reject a new idea. And this is basically dependent on the workload also, right? On some workload, the headroom may be huge. On some other workload, the headroom may be small. Yeah. So again, special purpose may be a good way actually to enable these ideas also, because on some special workloads, if you use heuristics to do memory scheduling, your performance is terrible, and there's a huge headroom. And if you use machine learning-based memory controllers, let's say, your performance is much, much better. You get, let's say, 50% of the headroom. Does that make sense?
Yeah, I think so. So yeah, I guess I was asking about headroom, and then the answer is that it depends on the workload. Mm-hmm. But I guess in the choice between human and data-driven, the data-driven will ultimately win because that's the only thing that allows you, I guess, the flexibility to adjust to the situation.
Exactly. You basically enable some other things like adaptivity to different workloads, changes that is very difficult to enable with humans. I mean, humans can also decide heuristics, right? Humans can design multiple policies for workload classes, and you switch between one policy to another policy. But it becomes harder and harder for a human to decide what a good policy is. Yeah. And some of these machine learning approaches, as they're examined, they may actually lead to better heuristics over time, right? We don't know if we can understand what the machine learning approach is doing. That turns out to be a problem, a difficulty with machine learning approaches, because they're usually black box, right? If you take reinforcement learning, it makes some decision at a given time. But it's very difficult to truly understand how it arrived at that decision, right? It'd be good if we can actually enable more methods for explaining how machine learning agents make the decisions that they make and how they arrive at that state, so that we can glean some insight and maybe develop better heuristic policies, right?
The motivation for that is just that heuristics are cheaper than
potentially, yeah. Potentially they're cheaper, absolutely, yeah. So I think these have synergies also. It's not just heuristic versus machine learning and they're opposed to each other, but you can gain insight from one to improve the other. Okay, these are very good questions. Okay, so now let's jump into some topic that's related, but that's more general. And we've seen this topic actually when we talked about memory performance attacks, but I'm going to be more general, and then I'm going to now discuss solutions to it from within the context of memory scheduling. But before we jump into, again, some review of memory performance attacks, let's talk about shared resource design. Remember, I showed you this picture multiple times. And if you look at this picture, this is an old multi-core picture. You can see the cores, right? Other than the cores, everything else is shared resource, right? You have shared interconnects, shared caches, shared memory controllers, shared memory, shared storage, many shared interconnects that connect all of those components. So most of the system is dedicated to storing and moving data. We discussed this, and almost all of that is really shared, right? Except for these core components that I pictorially shown over here. And even if you look at the core, if the core employs, for example, a multi-threading technique, just like GPUs do and many CPUs do today, even that core is shared. Even that's a shared resource between different threads that are running concurrently at the same time inside the core, right? So everything is shared, I would argue, in an existing system. And you really need to think about these hardware resources as shared resources. Some of them, of course, are more shared than others, right? If you go to the memory controller, if you have a 1,000 core system over here, if you're running 1,000 threads are trying to access this memory controller and disk, maybe storage is accessed by multiple different, let's say, chips over here. So you see one, but there could be another one, and there could be another one. So as you go outside in the system, there's more sharing going on. So I think it's good to think of systems as all shared resources and design policies that work with shared resources. And so, okay, why do we do resource sharing? Clearly, instead of dedicating a hardware resource to a hardware context, which is a thread that could run on hardware, right? Allow multiple hardware contexts to use it. It could be functional units, pipeline, caches, buses, memory, interconnect, storage. And you can also think of power budget as a shared resource, right? The battery life as a shared resource. And these are actually maybe not hardware resources, but they're as real, right? You don't want one thread to hog your power budget or your energy. Or if you actually are really forward-looking, maybe lifetime reliability, right? You have some lifetime reliability constraint on this, which who gets to hog it, let's say. Maybe you have some application that Apple is running on this, for example, and it's hogging my lifetime reliability, right? I don't want it. It's not providing me any benefits, but it's wearing out, I don't know, some resource. SSD comes to mind potentially, right? So that's also a shared resource if you think about it. Anything that's used by multiple, let's say, applications and that affects other applications in the short term or the long term is really a shared resource. And I like thinking of it that way. So, okay, why do we want to do resource sharing? Clearly, it improves utilization and efficiency, right? Meaning it leads to higher throughput overall. When a resource is left idle by one thread, another thread can use it, right? And there's no need to replicate the shared data if you're sharing caches, for example, between resources, between different threads. So as opposed to doing nothing, right? Basically, as opposed to replicating the resources such that the threads don't share resources at all. That is not efficient, clearly. It reduces communication latency. For example, shared data can be kept in the same cache in a multi-threaded processor or in a multi-core processor, and the different threads that need the same shared data basically get that from a shared resource, hardware resource. So conceptual sharing of data, programming level sharing of data can benefit from physical shared resources also, clearly. And it's, as a result of this is compatible with the shared memory model because in many systems we have shared memory model, programming and execution models, and physical sharing aids that clearly, right? If you didn't have physical sharing of resources across different processes, providing the shared memory model requires some additional system level and hardware level help, let's say, so that you can give the illusion that whenever you access this shared memory at the programming model level from this thread, this other thread also sees it, right? So somehow you need additional resources to enable that if your physical resources were not shared. That's why I think this is also important. Okay, so there are clearly benefits, and we know some of these benefits, right? Utilization. You don't want to run, let's say, 1,000 cores. You don't want to design a 1,000-core processor and have only one thread running on it because that's not efficient. That was my example earlier. But resource sharing clearly leads to disadvantages also because it leads to contention for resources. When a resource is not idle, another thread now cannot use it because somebody else is using it, right? Because you're doing resource sharing. And that's in time, basically. But the same also happens in space. If the space that is shared is occupied by one thread, then another thread needs to reoccupy it. Basically, threads can displace each other's data from the cache, for example, or from main memory, or from storage, if those are all shared media. Right? So basically, resource sharing results in contention for resource in time as well as space. Okay, and clearly this leads to reduction of some threads' performance, or both of the threads' performance. In fact, if you think about the memory performance attacks example that we gave, if both threads are accessing the same bank, both of the threads' performance can reduce significantly, right? If they keep causing bank conflicts to each other. Assume that they're not streaming, they're both random access. Well, assume that they're streaming to some level, let's say. Streaming is usually, you lose performance even more, right? But somehow you keep switching between the row buffer, between the two different threads. As a result, when run alone, they have some good locality, but when run together, their locality gets destroyed completely. As a result, both threads lose performance compared to when they're run alone significantly, right? And that doesn't sound good. Basically, thread performance can be worse than when it's run alone, and all of the threads can lose. And this also, resource sharing, as we discussed, eliminates performance isolation. This we didn't discuss a lot, but this may lead to inconsistent performance across runs. You run your program, you optimize your program heavily for a system, thinking that, oh, your program has the resources on the system. And then you run it once, you get some performance because it gets executed with some program X. You run it again, it gets some other performance because it gets executed with program Y. And these could be completely different performance numbers, right? So if you're looking for some performance isolation, meaning I should get this sort of latency guarantee, you may not get it, assuming there are no quality of service mechanisms implemented, right? Basically, thread performance depends on co-executed threads. And uncontrolled free-for-all sharing resources degrades quality of service, as we have seen earlier, right? This causes unfairness and starvation. So I'm going to go through this relatively quickly since we already seen memory performance attacks and discussed it in detail, except we didn't discuss the solutions. So this lecture is about some solutions and solution directions also. So basically, if you want to do resource sharing, you need to efficiently and fairly utilize the shared resources. If you don't want to do resource sharing at all, you're in an inefficient place, right? How do you actually enable no resource sharing? That's a bit difficult, right? Every application gets its own cache, gets its own interconnect, gets its own storage. You can partition everything very carefully, but you need to make sure that nothing is actually a weak link, let's say, in terms of quality of service. So if something is shared, that may actually be determine the performance of that application. Okay, so let me give you an example problem with shared caches. Clearly, we've seen memory controllers. Let's take a look at caches. This is a blue thread, T1, that's running alone. It occupies this much L2 cache space, let's say. This is an orange thread, T2, that's when it's running, it occupies this much L2 cache space. And when they're run together, this may not be the best example actually, but I had slides that are made by the authors of this work that I'm using clearly. When two threads are running together, basically this thread seems to get a lot more cache space. And assuming that these threads equally benefit from equal amount of cache, clearly you're unfairly degrading the performance of this orange thread in this case. That's the assumption, of course. But another example is, imagine a thread that has very good locality in its cache. It requires only 100 kilobytes of cache, let's say. And imagine another thread that doesn't benefit at all from cache, because what's doing is it's streaming through 10 gigabytes of data. It's touching every cache block only once, streaming through 10 gigabytes of data. So if you run these two threads together, and if you don't do anything careful in your caches, what will happen is the one that's streaming over huge amounts of data will destroy the caching locality of the other thread that has very good locality, right? Because it would keep displacing the blocks that are in the cache that are brought by this thread that has good locality. So that's an example. So in fact, if you don't have good reuse and if you keep streaming through memory, those are actually quite unfriendly to cache-friendly workloads. Okay, so it's kind of a similar example as memory performance attacks at the cache level. Okay, so clearly that needs to be handled in different resources. Okay, so why is let's talk about some meta questions. I think we talked about these also before, but let's go over it quickly again. So we want quality of service and shared resource management, as I asserted that, let's say. But why is unpredictable performance or lack of quality of service bad? First of all, it makes programmers' life difficult. An optimized program, you may actually work really hard to optimize your program. And even then you get low performance because your performance varies depending on corunners. Some corunner basically destroyed all of the caching optimizations that you've done. You assumed you had the cache for yourself. Well, too bad, that's not true. You optimize your program for it, but some other program that you have no control of destroys your performance. So basically, programmer optimizations become, let's say, worthless if you don't provide quality of service. It causes discomfort to user, clearly. An important program can starve, and we've seen this. And this is true for software shared resources also. I have interesting examples here, actually, in software resources. Working at a company like Microsoft, you see a lot of examples on how software is built. But at one time, I don't think this is true at this point, but at one time, Microsoft Office programs, Excel, Word, and PowerPoint, they used to have a shared access to storage, for example. They had to all go through the same, let's say, interface that's shared, software interface that's shared to go to storage. And if one of them was hanging for some reason or taking a long time, the other couldn't work very well. So you used to run into these really bad hanging of threads because one thread was accessing storage in Excel and your PowerPoint couldn't function well, or your Word couldn't function well. this is an example of resource sharing and denial of service from a software perspective. You designed your software to have the shared resource, and all of these programs are utilizing the shared library, let's call it. And because your library doesn't provide quality of service, one program gets denied service when it's accessing that library, whereas another program is making, well, maybe making progress. I don't know. It could actually, there could be bugs in that also, right? Okay, so clearly this is a problem with when you're writing software also. And it makes system management difficult also because, for example, if you want to enforce a service level agreement, but you cannot control the hardware resource sharing, how do you do that? So you're basically running, let's say, 100 programs. You want to put all of them on a single core machine, a single multi-core machine. And how do you guarantee the performance of all of those programs at the same time? Because you have no control, there could be all kinds of denial of service happening. As a result, you may not reach service level agreement guarantees. And because of this, many cloud providers, if they have an important service level agreement, let's say if they needed to guarantee some latency guarantees, for example, they wouldn't co-locate those programs together with other programs. So they basically dedicate a machine for this program where the service level agreement guarantee is, let's say, strong. Maybe it's an important customer. Maybe it's an important program that needs, let's say, low latency for some definition of low latency in the service level agreement. And this clearly leads to low utilization. So people are talking about data centers not utilized very well, right? Why? Because of this, basically. One of the reasons is because of this clearly. Because you cannot co-locate programs on the same multi-core machine. You have a 32-core machine, and today clearly we have even more cores. You have a 32-core machine, but you cannot run, let's say, even 2 applications together because you have this one application that's really important that requires a service level agreement guarantee. And you cannot provide that guarantee if you put another application next to it. So basically you're utilizing your system terribly, 1 out of 32. This is of course a rough estimate, right? Your system utilization is 1 out of 32. So why your data center is not utilized? This is a big reason actually. So if hardware actually had quality of service mechanisms that provided some of that control, then the system management overall would become much more efficient and clearly controllable at that point. So this is something actually very interesting. This because there's a lot of data that shows data centers have very low utilization, and it's really about the scheduling of jobs onto the machines. And if you cannot schedule jobs concurrently onto the machines, then basically utilization goes down very, very quickly. Yes.
Yeah, just wondering if there is existing or emerging technology that can let a program to tell whether some data is going to be used later. For example, for the streaming program, if a program can say, I'm not going to use this data later. Yeah. So is there some technology already existing or emerging?
Well, people actually have looked at that problem a lot, basically. Can the programmer or the compiler figure out what's going to be reused or not reused later? And can you provide some hints to the hardware such that the hardware distinguishes between that data that's going to be reused later and not reused later, or that's going to be likely to be reused later? And yes, there are actually hints that are provided in the ISAs, instruction set architecture. For example, x86 architecture has these temporal, non-temporal hints. If you know that you're not going to use your data, you can actually append your load with a non-temporal hint saying that it's not going to be used anytime soon, basically indicating that. And the architecture can use that hint. So it's possible to do it today, actually. And there's a lot of work on reuse prediction in compilers, for example. How do you predict the reuse? It's also done in hardware, in caches. We didn't cover caches, and I'm not sure if we will ever get to cover caches more in this course, but actually we covered it in digital design and computer architecture, but probably you didn't take it. You might want to take a look at the digital design and computer architecture courses where we covered caches. But caches also try to predict that sort of reuse in hardware. Yeah. Okay. Any other questions? Okay, let's move on then. So basically, to summarize, resource sharing clearly improves throughput. It gets better utilization of space. Partitioning provides performance isolation and predictable performance and the other benefits we discussed by giving dedicated space to a given program. The question is, can we get the benefits of both? And the idea here is to design the shared resources such that they're efficiently utilized, controllable, and partitionable. Hopefully, this way, you have no wasted resource, because if you do partitioning, you get wasted resources. But if you do sharing, hopefully you have no wasted resource if you do good scheduling. And but you need quality of service mechanisms for threads so that you can get the benefits of partitioning. And that's the idea, basically. And as we've discussed, memory system is a major shared resource. Another picture, you can see that essentially everything is shared. If you look at the core, it's also shared by different threads. And threads requests interfere in the memory system. And we've already said this, basically. Okay, so basically the problem is threads share the memory system, but memory system doesn't distinguish between threads requests. So this was the case, let's say, in 2006 or so, when we were doing experiments with memory performance attacks. This is much better today because of all of the research as well as development that has happened. There's more in real systems to provide quality of service, but I don't think it's still at the level that we want. So I'm going to give you kind of a history of that. So at the time, existing memory systems were free for all. They were shared based on demand, and control algorithms, as we discussed with memory performance attacks, for example, were thread unaware and thread unfair. As a result, aggressive threads can deny service to others because the system doesn't try to reduce or control inter-thread interference. And you know this picture, so I'm going to go through this relatively quickly. And you know why it happens by now. If you have these different types of applications, if you have an unfair memory controller, it can basically prioritize one application for a long time. And I'm going to go through this quickly because we've discussed this a lot, right? We call this a memory performance hog, for example. And this was a control application. And memory performance hog essentially destroyed the performance of the other application because memory controller scheduling policy was fundamentally unfair, right? And you could do this maliciously, you could do this non-maliciously. It's the same thing in the end. It could be a denial of service threat or a quality of service problem. And in fact, these are two sides of the same coin, right? Whenever you have a quality of service problem, it could potentially be exploited for denial of service. Someone, let's say, malicious, can basically turn that into a performance attack because there's an unfairness problem, lack of quality of service, right? And these are slides that we covered, so I'm going through them quickly, right? It's an example resource, right? DRAM controllers. Since we've seen it recently, it's good to revisit it again. But the policy we discussed is unfair because it unfairly prioritizes threads that keep hitting in the row buffer. It also unfairly prioritizes threads that have a lot of requests in the memory request buffer, meaning more memory intensive threads. Okay, yeah, and these were some results that I showed you in an earlier lecture. If you have questions, feel free to ask, but I'm going through this quickly because we can get to some new material, right? So basically, this becomes a greater problem with more cores because there's more requests in the system and the delays increase because of that. And as a result, it causes all these problems that we have discussed earlier. It also leads to low system performance. So this is also important, right? Whenever you talk about fairness, sometimes people have I don't know where this comes from, but people have the notion that fairness directly goes against performance. That's absolutely not true, actually. Fairness actually can lead to better performance, overall performance. As we have discussed in an earlier example, right, in the past. And I'll show you even more results today, basically, with more fair policies, you can get even better performance, overall system performance. So I don't know why this notion exists. Actually, I tried to find it, but does anybody know why this notion exists? Why do people think fairness is actually bad for overall throughput or performance?
Might be coming from the networks background. there okay. I think it's almost universally true.
I don't know. I don't buy that. I think networks, okay, maybe we can discuss this, but if you look at the end-to-end application performance, even in the networks, I don't buy that fairness goes against overall performance, overall system throughput. If you look at an individual router, yeah, it's hard to see this. Individual router is not the whole story, though.
Yeah, yes.
Individual router throughput, yes, maybe your throughput, if you look at basically local component metrics, yes, fairness hurts those actually. Absolutely, I agree with that potential. I don't see that absolutely clearly in the networks. But for example, the memory controllers, if you're more fair, you're going to reduce the data throughput in the system, yes. But that's not your metric for performance, right? That should never be your metric for performance. Your metric for performance is, well, okay, one more reasonable metric for performance is how quickly you can finish all of the applications you have in your hand. That's the application level throughput. I don't care about how much memory bandwidth I'm utilizing. I could be utilizing only 10% of my memory bandwidth. I don't care as long as I can finish my application much faster, right? Does that make sense, Joel?
That makes sense. Of course, that's not really what networks people are dealing with applications.
Absolutely,
They
and
look
I don't
at
like it.
the throughput.
And in fact, if you, I'm going to talk about a work where we actually talk about those network fair queuing mechanisms. And basically we say exactly what I just said. They don't talk about applicational performance at all. They talk about router performance. Yeah, but that's a very myopic view, right? This router is one router out of thousands of things that my request goes through. And in the end, what I care about is my application, how fast I can finish it, right? Yeah, that's a very good point. I think now I remember, very good. You reminded me why this misconception exists, I think. I think misconception exists because you're not looking at the problem holistically, globally. You're looking at the component. And this is an example, I think, maybe of a component-aware approach. I didn't think about this before, but people are so focused on components. Let's optimize the performance of this router that they're losing the big picture, which is basically they're seeing the trees, but they're losing the forest. They're in a big forest. You optimize the forest, not a single tree, right? Okay, maybe this stall time fair memory scheduling remind me because we actually exactly make the same argument over there. And okay, let me move on. Okay, and even in network systems, I mean, we have actually similar results, but maybe one of the reasons that's the case in general networking is people don't have very good mechanisms to do end-to-end performance studies. But that's what we do in architecture, right? End-to-end performance studies all the time. That's why I think even if your architecture is like network, packet switch networks like this that I've shown you earlier in the past, if you improve fairness and quality of service, your performance also improves. And again, this paper shows that actually, if you look at it. Okay. I mean, at some point we may cover on-chip networks actually in this class. You will see this more, but basically what's happening here is you have 64 cores and each core has a router. And basically whenever you need to send a request from this core to this memory controller, for example, you go through packet switch routers. It's very much like a network, right? Except it's on chip. And why have people propose it? They propose it so that the systems become more scalable, right? But you can think of it as a distributed system on a chip. And again, you run into a very similar quality of service problems like the memory controller that we saw in each of these routers over here. But again, your goal may be to optimize each router, but that's very myopic. Your goal should be to really optimize the entire system. Okay, so we discussed memory performance attacks. I'm not going to harp on it more. And this is another paper you may want to read that is of similar nature. That's a quality of service mechanism. And to be on the light side a little bit, I will introduce Maslow again. You guys remember Maslow, hopefully, right? Maybe you're bored of him right now. I'd recommend reading his work also, although it's a totally different area, right? But it's always good to read different areas so that you can enhance your knowledge. But of course, I play games with Maslow, as you can see, and with this hierarchy of needs. And in this case, the game is this: lack of quality of service can be a safety and security problem, right? And I will assert this. And I think this is true, actually, because as I said, lack of quality of service, of course, if done badly, for example, if you run a life-critical application together with a not life-critical application, and you don't provide quality of service, predictability to the life-critical application, that life-critical application can get delayed, and as a result, someone could die, right? This is, of course, an extreme, but people are actually thinking about this. For example, in airplanes, right? It's clearly a safety-critical thing. In airplanes, there was this argument for some time, especially when multi-core systems were coming. They basically said, oh, why don't we centralize our resource in an airplane? So I said, everything runs in a small data center in an airplane. Of course, it's not a data center, but it's a small set of servers in an airplane, right? And the argument is, yeah, you have a lot of capability in a server because it's multi-core, and this can process anything, right? Including the safety critical functions of the airplane, right? Now you're actually running safety critical functions plus 200 passengers watching whatever on their screens, right? Which one's more important? Clearly, one of them is a bit more important, right? The safety critical functions for flying the airplane, checking if something is wrong. And there are many, many safety critical functions in an airplane, right? Then the question is, can you actually, okay, maybe it's a good idea, maybe this improves efficiency, but can you actually make sure those safety critical applications do not get affected, right? And that becomes the hard problem at that point. Because now your network is shared in the airplane, your physical medium is shared clearly, memory is shared, storage is shared, everything is shared basically between those applications. And how do you guarantee that this is not going to be a problem for safety critical applications? And this is exactly an example where if you don't provide quality of service, and this is a very strict quality of service, I should say, it's actually what we're going to discuss is more softer quality of service. But if you don't provide hard quality of service for safety critical applications, then resource sharing could become a big problem. Okay, take airplane, replace it with self-driving cars, same thing, right? You can be running your brake controller or pedestrian detector together with your, I don't know, DVD player that someone is watching in the back. Yeah, basically there are a lot of examples. So cars are actually, and these are arguments actually that are discussed in these industries basically. For example, when multi-core systems were being deployed heavily, a lot of car companies were quite excited. They can reduce their cost, right? They have all these 500 microcontrollers, which are increasing in their cars. Why don't we have a single or two or three, whatever, multi-core system and replace all of our microcontrollers? That sounds good in theory, but in practice, if you don't have, basically you run into the quality of service problem. Yeah. And if you solve the quality of service problem, maybe you can make it happen. Okay, so now let's try to solve the quality of service problem. But again, I'm not going to do very hard quality of service. Hard quality of service is you have a deadline, you have to meet that deadline. If you miss it, you're either dead or you have some serious issues, right? That's very hard, right? So we're going to try to be soft, although we're going to make it hard toward the end, if you have time for it, for deadline-oriented hardware accelerators, for example, or deadline-oriented applications. But let's start first. So clearly, we have many resources, and I just mentioned 3 of them here because we're going to cover especially these 3. But today, we're going to focus especially on the memory controller. But never forget the interconnect and caches, and also other stuff that we discussed earlier. So basically, if you want quality of service, you need to control the system, meaning you need to design an interference-aware or quality of service-aware memory system. And then I think there are 3 major high-level questions in any quality of service-aware system. Even you can remove the memory over here, basically, quality of service-aware system in general. First of all, how do you reduce the interference between different applications or threads or virtual machines, whatever you're trying to provide quality of service to, right? How do you control the interference between those entities? And how do you make the system configurable so that you can enable different quality of service policies, right? Okay, so the first one is actually important because if you reduce the interference, hopefully you're improving system performance and core utilization, right? If you reduce the interference, cores are making better progress. As a result, your performance hopefully improves as well. And also your requests become serialized less and cores starve less. So this is usually good for reducing inter-thread interference is good for performance in general, and also latencies. How do you control inter-thread interference? I think this is important. Controllability is important because this provides mechanisms to enable system software to enforce quality of service policies. Again, now we're going to talk about hardware, but hardware needs to be controllable a bit. Of course, you need to provide high system performance while doing this. Whenever you're controlling inter-thread interference, one way of controlling it, for example, could be saying there are multiple cores, 4 cores, and you basically say only one core can inject requests in these, let's say, 1,000 cycles. This is called core throttling, let's say, right? You're basically throttling the cores and you're giving time slots to different cores to inject requests. This may be okay, but it reduces system performance significantly. This sort of throttling policies, unless they're done really correctly and well, you can reduce system performance a lot because you're reducing utilization of the entire system. And the one I mentioned to you, you basically round robin across cores, and even at a fine grain, well, let's say 10,000 cycles, each thread can inject requests only in these 10,000 cycles. Nobody can inject during that time. This may sound a bit fair, right? And maybe for some definition of fairness, it's fair. We'll talk about definitions of fairness also. But this is terrible for performance. imagine you have, again, even a 4-core system actually loses performance a lot because there's a lot of fine-grained memory requirements of threads. If you say 3 of these threads that are running should not inject, let's say, every 3 out of 4 cycles, 30,000 out of 40,000 cycles, then basically you're really denying service to all of those threads for a long time, and you're reducing the system utilization a lot. So you should always think about, basically, whenever you're designing a quality of service policy, you should be careful because you may be destroying system performance if you're not careful. Okay, so fairness does not always improve performance, as you can see, right? It really depends on the policy that you design. So your goal should never be just fairness for the sake of fairness, in my opinion. Like the example policy that I show you, I think, is fairness, basically without knowing what you're doing, maybe. I would argue that. As a result, you may actually destroy performance, sure. Okay, so and the last one is configurability. And I think this is really important because the policies need to change, right? Meaning you don't always have a single goal in a system, unless it's an extremely specialized system. Especially in a general purpose system, you need to be flexible. You want to have flexible mechanisms that can achieve many goals. So basically the mechanism needs to be configurable so that different policies can be constructed and built on top of it. For example, sometimes you don't care about fairness. Sometimes the operating system wants to run applications that have no fairness or latency, etc. requirements, just run free for all. I'm not suggesting this is always a good idea, but because sometimes if you're denying service, your performance also gets destroyed, right? But maybe the operating system or the user knows something about the running applications. They're not going to interfere with each other, so just let them go, right? And that's a reasonable policy to enable, right? You don't want to dictate policy for the user. You just want to build the underlying fairness mechanisms that can be configured by the user or the operating system, basically. Sometimes you need strict guarantees, and there are different kinds of guarantees that different applications have: latency, throughput, etc. So basically, the mechanisms you build into the hardware should be configurable enough such that the policies, such that they can enable many different types of fairness and performance policies or quality of service policies in general. And I think this is a difficult part, actually. It's not, I mean, all of these are not easy. You need to think deeply about the resources that you're designing clearly. But making things configurable and flexible enables providing the right knobs to the operating system or the user such that they can control the knobs, so that they can construct a policy that makes sense for them at a given point in time. Because their policies may change also depending on the application mixes that are running, right? Okay, I spent a lot of time on the slide, but I think these principles are actually really important for any quality of service aware system. Even if you're not talking about memory system, even if you're talking about software that is sharing resources, I think these all apply. Okay, now let's take a look at some approaches, and then we're going to go into a bit more detail. So I think in general, there are 2 approaches to designing quality of service over memory systems. Again, this could probably be generalized as well, but I call one of these smart resources. Smart resource means, so, okay, the baseline is you have some resources and you have some policies that are component aware, right? That's usually how design works. That's what we discussed earlier. Yeah, memory controller, it has some policies internally. You have a cache, it has some techniques to decide which cache block should be cached, which cache block should not be cached. How do you prioritize the cache blocks, etc. Make it more smart. So what does that smart mean? Design each of these shared resources to have a configurable interference control and reduction mechanism. That's the idea, basically. And you need to go and visit all of these resources one by one to enable that. This has now become resource specific clearly. And I think this is important to do. And we will do it in the context of memory controllers today. The second approach, which is orthogonal, but I think complementary also at the same time, is dumb resources. Meaning, okay, somebody designed these resources as they are. They're terribly unfair, like the memory controller that we discussed. Keep it like that, but design some mechanisms around these resources such that you can control the injection of requests into the resources, or you can control the mapping of data across different resources so that you can basically reduce and control interference, and you can do it in a configurable manner. Hopefully this makes sense, right? Basically, you have these memory controllers, caches, interconnect that's shared. Keep the resources as bad as they are from a quality of service perspective. Don't change anything. let's say, but do source throttling, meaning observe what's going on in the resources somehow, and basically control the injection of requests into the resources such that you minimize the interference or control the interference, basically. And hopefully we'll have time to see this, but probably we will not get a chance to talk about it. But this is a way of actually controlling interference clearly. And this is one way actually that's employed in the internet. We were talking about networking before, right? Congestion control in the internet happens this way, basically. Different sources that inject requests onto the internet back off and control. If there's a congestion signal, let's say, from one router that gets propagated to the sources or other routers, and sources that are transmitting requests basically back off for some time. And if you don't do this carefully, this leads to very bad throughput losses overall in the system. If, for example, you throttle an application for much longer than they need to be throttled, you're losing utilization, right? Okay, another example is data mapping to memory controllers. So for example, if you have multiple memory controllers, you can map the data to different memory controllers such that applications that interfere with each other don't interfere with each other, right? If they are mapped to different memory controllers. If you do the mapping, let's say intelligently, meaning you identify which applications are bad to schedule together to the same memory controller and separate them from each other, then this could be actually a very good policy. Of course, this also comes at a cost, which is memory capacity, right? How do you actually use the memory capacity and bandwidth? How do you actually use the whole memory capacity of all memory controllers as well as memory bandwidth of all memory controllers? So this leads to load balancing problems. Whenever you partition or try to map the data separately such that you reduce interference, you run into load balancing problems in terms of both capacity and bandwidth. And again, if you're not careful, this could lead to bad performance also. But there are example techniques that show that if you do it carefully, this could actually improve performance significantly. And finally, the last one is thread scheduling to cores, right? Basically, you can schedule the threads that do not interact with each other badly together at the same time. Of course, this requires you to have an access to a thread pool, let's say, that's heterogeneous enough so that you can actually do the scheduling nicely. For example, I showed you the cache example earlier, right? One very streaming thread, heavily streaming thread, accessing lots of data can destroy the performance of another thread that has very good locality in the caches. If you know this information, if you profile it, or reactively, if you figure out this information, you learn or memorize, let's say, and then over time you basically say, okay, I should schedule this thread with another thread that also has bad cache performance or something like that, right? Basically, I never schedule two threads that are going to interact badly with each other in the cache. Of course, while doing this, you should be careful that you don't destroy what's happening in the memory controller also, right? So you need to really do this carefully also. Okay, I think these are quite interesting, clearly. Probably we will not have time to cover them, but I will point you to some lectures. We will cover memory controllers because I think it's very interesting case study given what we have been doing so far. And remember that these can be combined, actually. There's nothing that says, oh, you cannot have smart resource, and on top of that, this sort of control in the boundary of the resources, let's say. And whenever you combine them, of course, again, you need to carefully combine these techniques. You can get better performance as well as better quality of service. So in the end, I think the more complexity managed carefully leads to better performance and better quality of service. And we have seen it in the results that I'm not going to talk about today. I think while thinking about this, it may be also good to think about how can you do this in a more automatically, right? I'm going to talk about a lot of heuristics today, but I think there's a lot of room for doing it more automatically using machine learning techniques, for example. Okay, so I think I already discussed this, but there are 4 fundamental interference control techniques. If you come up with another one, let me know. One is prioritization or request scheduling, which is what we're going to cover today. Basically, you're given some sort of requests, they're sitting on your request buffer. How do you prioritize it? The other is data mapping to different banks, channels, ranks, or maybe other DRAM components that we discussed, subarrays. It could be even finer granularities, so that you can reduce interference and control it. Core or source throttling, we discussed that also. And finally, application or thread scheduling. And if we had all the time in the world, we would cover all of them, but let's start with the first one. Okay, I think I'm anticipating that we're not going to be able to cover all 3 of these over here, but they're also important. So if you're interested in it, you can find a lecture that covers them. So for example, this is one technique, application to core mapping, that tries to reduce interference, improve locality, improve bandwidth utilization by doing better load balancing, for example, as we discussed, and some other techniques to reduce interference even more for applications that really care about being isolated, meaning applications that whose performance get destroyed if you don't isolate them. And then some other technique that we're not going to talk about over here. But you can see that there you can employ multiple of these techniques together as well. And I guess this is probably, I will draw this curve. I put it over here so that I don't forget to draw this curve because it's a very important curve. Have you guys seen this curve before? This is called the load latency curve. Nobody took a networking course? Yes, and you have seen the curve? Okay, somebody who took a networking course, I guess, seen the curve. Maybe I will cover this curve because otherwise I may forget covering it. So let's see. So can people see this on Zoom? Zoom
Yes.
people?
Yes,
Yeah.
yes.
But is it clear?
Like the image is fine, yes.
Yeah, but is it small or is it big?
It's not maximized. No, we can see
Okay,
YouTube
so-
around it.
Okay, yeah, I don't like that. So let me try to, because there was a way to actually, and this is a good test also. And I have no idea where my Zoom went. Now, when you want that thing over there up, you cannot find it. Amazing. Okay, yeah, if I press escape, it comes, I guess. So how did I do this? Anybody? Okay, oh yeah. Somebody knows better than me for sure. That's good. So which one? Is it content from second camera? Okay. Okay, can people see it?
No, now the screen sharing is completely gone for me. We're just seeing your camera now. Like
Oh,
the
you're
laptop
seeing my
camera.
camera. Oh,
Yeah,
okay,
yeah.
okay. Switch camera. I need to do that. Okay, is this better?
Yeah, but now there's no screen sharing anymore.
Yeah, you don't need the screen sharing at this point.
Oh, okay, good.
This was my goal. I think we kind
Okay,
of
good.
achieved this, but I don't know why this is so small in that camera. But anyway, it's better than nothing. Okay, so finally we figured out what's going on, I guess. But okay, I think this is very fundamental to any resource, not just network. So basically, you have this load latency curve. Let me see how this looks. Okay, I'm kind of in the middle. So this is called the load, and this is called the latency. And this is usually a measure of how, let's say, contended a system is. This could be expressed, for example, in terms of injection rates, request injection rates. Basically, how many requests per cycle each source is injecting into the system. And you can think of the system whenever you think of a shared resource system. It's good to think of something like this. Basically, you have these sources. Yeah, okay, you could keep doing this forever, I guess. And these are the shared resources, right? They have shared resources, you have all these sources, and they're communicating in some way with each other. And in case of main memory, they're communicating with main memory also, right? And each of these sources are putting some load into the system, meaning they're injecting requests into the system. And usually people look at how latency behaves in this sort of system, right? And normally what you have is there's some minimum latency. Basically, you start with. That's dependent on the design of the system, basically. Whatever policies you have inside the hardware, the length of the interconnects, the length of how long it takes to access DRAM, there's some minimum latency that you cannot go below, basically. And if your load is 0, you're at this point. And if you keep increasing your load, I'm not going to give you exact numbers clearly here because it really depends on the design of the system. Basically, your curve looks like this. And this is a very fundamental curve. Basically, at some point, this is called this asymptote over here is called the saturation throughput. At some point, basically, your latencies shoot up and your network completely gets, I call it network because you can think of this as a network, but your shared resources completely get saturated. This means that you have just too much load on the system. You've allowed too much injection into the system. Your system basically cannot satisfy the requests in a reasonable time, let's say, right? Your latency shut up. Oh, if I have more colors over here, I could do more, but I don't have more colors. I guess having another color of the same, another chalk of the same color doesn't help, right? Okay, so maybe, so basically, usually, this is a region where you don't want to operate on. Okay, maybe it depends on your tolerance, right? That's not a good region, basically. You have too much load on your system. So how do you fix that problem? Well, go to this region, right? How do you go to that region? Well, one way could be to reduce the injection rate into the system. So basically doing source throttling, like we discussed, can move you from here to here, right? That's the idea. So this here, maybe you have a maximum tolerable latency, right? Depending on your application. And you can draw this curve for each application also, by the way. It could be for the entire system, for each application, etc. You could draw it for synthetic workloads, different access patterns with random accesses, for example. If all of your accesses were completely random, what would this curve look like for a given hardware shared resource configuration? If all of your accesses were streaming, what would this curve look like? If the communication patterns were different between these different entities, what would this curve look like? And people do these studies actually. Of course, those are synthetic. Real applications also show this behavior, but real applications are much more complicated than synthetic patterns, right? So basically, in the end, if you're there's a fundamental load level that your network or your system cannot tolerate without latency shooting up that high. And you don't want to operate in this regime. You want to put yourself to this regime. And again, the quality of service mechanisms can fix that, especially the second quality of source throttling. Changing the data mapping can fix it. You can move from here to here by changing the data mapping. Thread scheduling can fix it. Say, okay, I'm in this regime, I'm going to remove some of the threads. Clearly, that will hopefully bring you down over here. But usually, prioritization mechanisms may not be able to fix it, right? If all you're doing is prioritizing in the memory controller, for example, you don't have much control in this curve. I mean, you have some control, but you're basically dealing with whatever is thrown at you, right? Which is whatever is in your request buffer. So that's why these other techniques that we discussed that are less prioritization based are quite important actually. Source throttling, data mapping, thread scheduling. And again, I think I would like to think this as there are three regimes over here. I don't have a color, but maybe this is this is the really low load regime. Here, quality of service may not matter. This is really the medium load regime. Here, the quality of service actually matters a lot. Of course, it depends on where you bound these things, but quality of service matters a lot over here. Here, you're at the basically too high load, let's say. I should call this as the medium to high load over here. And maybe this is the too high load. Here, you don't want to be basically because you're pushing your system too much over here. And if you want to be over here, maybe you need to design a different system, right? And that design, well, we don't really have more colors. The world cannot consist of 3 colors, right? Okay, I don't see it, but yeah, okay. If you're over here, you really want to change the, let's say, policies in your system to put you maybe somewhere over here, right? Maybe add more resources, I don't know, add more banks to your memory controller, add more channels, add more caches, increase the bandwidth. And now your system becomes like this, right? Such that you reach your saturation throughput much later, right? Of course, this is probably the second one. The second system over here, system 2, is probably much more costly than system 1, right? Yeah. I mean, whenever you change the memory control policy, actually, you go to a different curve also. Maybe I kind of misrepresented memory control policies. Whenever you change the memory control policy, let's say you go to some other curve over here, like it may look like this if you have a better memory scheduler. But you're really not fundamentally changing, let's say, maybe this is too much, but again, I don't show you the exact numbers over here, just like a good industry presentation would do. They would never show you numbers over here. I'm just giving you the conceptual view over here. Yes?
I think I don't really understand why this plot is not a step function, because it seems like an asymptote exists because eventually you get to a point where you have more requests than your per second than your ability to service
Exactly, yeah.
unit time. And so wouldn't it just be like why the smoothness? Why wouldn't it just be like below a certain amount, you're like a low latency because you're able to service it, and past that amount, you have 1.0001 per second, whereas you only do 1 per second. And so eventually a steady state time will be infinite amount of latency.
Well, I cannot perfectly answer it, but I would say that latency is continuous, right? Latency is a continuous function because your queuing delay accumulates cycle by cycle. It's a step function of the cycle count, yes. But I think there's no reason to think that this should be a step function that's at a higher granularity than that, right? Because as you keep injecting requests, your latency keeps accumulating, and you're basically wasting cycle by cycle, let's say. That's why this curve is shooting up very quickly. So at this point, it shoots up very quickly after some point. That's why you have that asymptote. Make sense? Yeah. If latency was a step function, like if you were actually adding latencies in the chunks of 50 cycles, for example, this would look more like a step function, perhaps, yes. Of course, it depends on the granularity you observe this also. Okay. Any other question? I think there was another question in the back. No? Okay. Okay, yeah, I wanted to give you this curve, and that slide that I added over there was my reminder. But I think this is very fundamental. Like if we get a chance to cover interconnection networks, you will see this curve. For example, I mean, in the context of interconnection networks, maybe I'll draw this over here, but you have this basic thing. This is your minimum latency, right? This minimum latency is dictated by multiple things. You have a topology, you have a routing algorithm, and you have a flow control mechanism, like congestion control, for example. And all of them dictate your minimum latency. And depending on the choices you make in terms of topology, for example, if you have a bus or 2D mesh or butterfly interconnect, depending on the routing algorithm and depending on flow control, this curve may look like this for a given workload, or it may look like this, right? Or it may look with your minimum latency point may also be very different, right? Or it may look like this. So your design basically very much affects what these curves look like. And again, it's good to consider these curves based on specific workloads, right? In one case, like if you have random accesses, the curve may look like this. If you have streaming accesses, the curves may be different, right? So it's always important to consider the workload as well. Okay. So now that we've done with this, there's something in the chat. It says it's live now. It's probably obsolete. How do I get out of this mode? I go to more? No. Anybody? Oh, stop share. Okay, yes, thank you. That makes sense. Okay, let's share again. Basic. Okay, yeah, that's what this curve is about basically, but you cannot see it because I turned this off. And let's, okay. Okay, so we may get to see this a bit more in interconnection networks, but I think it's a good introduction right now. If you want to learn more about memory channel partitioning, I gave you the basic idea, but there's more to be discussed. So we're going to talk about quality of service over memory scheduling. Remember, memory control resolves memory contention by scheduling requests. And we're going to cover how do we schedule requests to provide high system performance, high fairness to applications, and configurability to the system software. And clearly, for this, memory controller needs to be aware of threats. I think this is a good time to actually take a 16-minute break, since this is a very natural boundary of the lecture. So I'm going to give you a lot of different scheduling algorithms and hopefully give you a historical perspective also. Unfortunately, we're not going to be able to cover a lot of, let's say, innovative, creative algorithms that are designed, but hopefully it'll give you a glimpse of heuristics. And these are all heuristics again, right? Keep that in mind. Okay, so let's take a 16-minute break. Let's be back at 51 past 2, and then we'll continue.
Honor, you still need your mic, I think.
Annoying but necessary. Okay, can you hear me now?
Yep, perfect.
Okay, excellent. Okay, yeah, what I was saying was we're going to cover a bunch of ideas. I'm not going to do that right now, but this is kind of an abstract that summarizes a lot of the ideas we're going to cover, idea and takeaway. And some of them we're not going to be able to cover since we don't have time, but I'm hoping that we will at least cover 4 or 5 of these. And you can see there's a lot more, right? So some things we're not going to cover is prefetching. How do you handle prefetches? Oh, because we didn't have a detailed lecture on prefetches, but prefetches are going to be important also in equality of service over memory scheduling. So you need to carefully control and prioritize prefetch requests. And yeah, if you're aware of the cache policies, you can design a much better memory controller. Basically, co-designing the memory controller and cache together is important also. But again, we don't have time. We will talk about non-volatile memory tomorrow, hopefully. And this is a problem in non-volatile memory also. This is a problem in GPU systems also. As I said, if you want to do hard real time, this is also a problem over there. And clearly, there are issues over there. But let's start with the first idea. So that was kind of an abstract of the ideas. If you want, you can go back and refer to them after we cover the ideas. So remember the memory performance attacks, right? And this is clearly a problem. And it's demonstrated on real systems. Then the question becomes, how do you solve the problem, right? And hopefully, we're going to see some ideas. And then this will inspire some other research that will do even more with memory scheduling. Let me turn. Okay, I guess this doesn't want to go down more. And this is the second paper we wrote, let's say, after we discovered this problem. And this is called stall time fair memory scheduling. And you've already seen this picture. Basically, we have an uncontrollable, unpredictable system. Memory control is shared, and it has an unfair policy. And this is the solution that we developed first, let's say. And I think it's a very interesting solution. It's called, yeah, I already said it's called stall time fair memory scheduling. And the goal, if you want to solve the slowdown problem, this picture over here, one way to solve is to equalize the slowdown of equal priority threads, right? If all the threads are equal priority, meaning of equal importance, why are you slowing some of them much more than others? Right? That's the idea. Slow them equally, at least from the memory perspective. And that's the idea, basically. Threads that are sharing the main memory should experience similar slowdowns compared to when they're run alone. And that's our definition of fairness, also in this case. And if you do this, you also improve overall system performance by ensuring cores are making more proportional progress. They're slowed down, let's say, proportionally, right? And the idea at a high level is very nice, I think. Memory controller estimates each thread slowdown due to interference and schedules requests in a way to balance the slowdowns. Okay, we're going to go into a little bit more detail. So it turns out it's not easy to estimate each thread slowdown in the memory controller. You can do it, but there's some error. But this paper shows still good results because it doesn't need to estimate the slowdowns perfectly. As long as it's good enough, it can still make the right decisions. So if you can estimate the slowdown perfectly, that could be good for providing predictable performance, right? If you can say, oh, this thread is slowing down by 2x at this time because you're running it together with these applications. And if somebody said that you should not slow this thread down by more than 1.2x, then you know what to do, right? Basically, at least you know what the problem is. You're slowing down too much compared to the goal. But we're not going to be able to do that in this particular work because our estimations are not that accurate. But let's take a look at this in a bit more detail. So this work introduces the notion of stall time fairness. This is the work that I mentioned, talks about networking, for example, and describes why network router quality of service mechanisms are not good to apply to DRAM systems because they're not taking into account the application performance, as well as DRAM systems have differences from a router. So if you look at the networking problem, usually you have a link and you want to request schedules on the link. And that link has no state. And that link is a single link. Whereas if you look at a DRAM system, so far you know very well that that DRAM system has state, meaning the row buffer. So that becomes very important. And it also has a lot of parallelism. It's not a single link. It's actually a more complicated system. It has banks, for example, right? It has a shared channel. So that's why it's different. It's a different problem compared to a network link. And also, as discussed earlier, usually those network works try to, they're myopic. They just look at a single router, a single link. They don't look at the entire application. We're going to look at the entire application running on a multi-core system, right? So basically, this was our definition of fairness. A DRAM system is fair if it equalizes slowdown of equal priority threads relative to when each thread is run alone on the same system. And we're going to define slowdown as memory slowdown because we're looking at just the memory controller, like not all of the shared resources. So we're going to try the memory slowdown, equalize the memory slowdowns. So, okay, let's go into a bit more detail. And you will see some of the difficulties popping up as we go into more detail. How do I, okay, this one. So basically, we define the DRAM or memory-related stall time of a thread as the time a thread spends waiting for memory. Yes?
So
I think it's not working, is it?
okay, I guess.
Okay.
So this is a fairness perspective from the hardware side, right? But if you think about the end user does not think of each application as, for instance, a music application should not slow down compared to, let's say, MATLAB. So that's, how do we consider users' priorities?
Well, I would argue that this is not about the hardware side. This is really what gets exposed to the user at some level. So it's really equal priority threads, right? Don't forget that equal priority. We're going to get back to that priority later. Make sense? Okay. Okay, if they're not equal priority, yes, we'll do something else later to adjust for that. But let's assume that everything is equal priority. Okay, DRAM related or memory related stall time is the time a thread spends waiting for main memory. And we have two metrics, two parameters. Two things that we calculate. ST shared, stall time shared, is the DRAM related stall time when the threads runs together with other threads. You can calculate this easily, right? How much are you slowing down due to memory when you're running together with everything else? You just count the cycles when you cannot make progress because you're waiting for some request coming from memory. You can do this in the core, as we describe in the paper. ST alone is DRAM related stall time when the thread runs alone. And memory slowdown is ST shared divided by ST alone. It's the relative increase in stall time compared to how much you're stalling if you're running alone. So it takes into account the inherent performance of a thread, right? Inherent stall time. Okay, does that make sense? Okay. So basically, stall time fair memory scheduler aims to equalize memory slowdown as much as possible for interfering threads without sacrificing performance. If the threads are not interfering with each other, it doesn't take any action actually. So it considers the inherent DRAM performance of each thread because it considers ST alone. And it aims to allow proportional progress of threads by equalizing the slowdowns. So it actually makes a lot of sense from a system level perspective also, because if you think about the system level perspective, the operating system schedules equal priority applications to different cores. It expects them to make, let's say, equal amount of progress, if you will. That's how the scheduling algorithms behave. And this is really proportional, basically proportional progress, I should say. Equal amount of progress depends on the application's inherent progress also, baseline progress. And we don't want to basically prioritize one application over the other without, if you don't take into account this ST alone, you may actually prioritize one application that's making very good progress, right, inside the memory system. That's why you need to normalize to this ST alone. Does that make sense? It requires more thinking, of course, but okay. So how do you actually implement this? Assuming that this is a good metric, and it's actually a reasonable first cut, let's say, you need to design a memory controller that tracks stall time shared for each thread, and this is easy to do. But the hard part is really stall time alone. You're running with other threads. How do you estimate the stall time of the thread if it were running alone? And this is an online estimation problem that is not easy, basically. So how do you estimate it? I'm not going to talk about it in detail, but you can guess, right? You basically, what we define in this paper is define excess stall time. So you have the stall time shared. You know that this is the amount of time you're stalling because you're running together with everyone. Some of that is inherent because you should stall when you're running alone also. So you can express stall time shared as stall time alone plus some excess stall time, extra stall time that you experience because other people are delaying you. right? So how do you estimate? It boils down to how do you estimate that excess stall time? So if you somehow estimate that excess stall time because you're stalling more because somebody else got scheduled, even though you had a request in the queue. Now you increment some cycles, cycle count saying, oh, okay, I've been spending these cycles waiting, even though, because somebody else got scheduled ahead of me, right, in the memory bus. Does that make sense? So you can basically count the cycles you're delayed because somebody else's request was scheduled before you. Of course, it's not that easy, right? If it were just a link, it would be easy. But now it's not a link. It has two problems. One is a row buffer. Somebody else may have evicted your row buffer entry because of the shared resources. And you could have easily got a row buffer hit if you were running alone. But now you get a row buffer conflict or row buffer miss because somebody else evicted your row buffer or the row that you would have kept open, right, in memory. So estimation of that is more difficult, clearly. So for that, you need to have shadow row buffers. What row would have been open if you were running alone? That adds more hardware cost. And you can make this estimation also reasonably well. But the really difficult thing to estimate is parallelism, meaning you have multiple banks in the system and potentially multiple memory controllers. Ignore that for now, but multiple banks. And you have one request that gets delayed by some other thread because that thread gets scheduled in one bank. But in some other bank, you have some other request that's going on. When you were in the baseline, when you were running alone, those two requests can be serviced in parallel in the banks potentially, right? But how do you estimate that parallelism becomes much more difficult actually? Because if you're running alone, you're using all of the system by yourself and you have some bank level parallelism. If you're running together with many threads, now your bank level parallelism changes in ways that are much, much more difficult to model, right? Because it's a very dynamic system, requests keep coming, going out, getting serviced. And how do you estimate what your alone bank level parallelism or overlapping of requests in the memory system would have been if you were running alone? This basically goes back to simulating completely what would happen if you were running alone, if you want to be completely accurate. And clearly that's not hardware friendly, right? That builds a memory controller that's imitating what would happen if each thread were running alone. Right? So if you look at the paper, there are some heuristics to estimate this parallelism factor. In fact, it's called a parallelism factor. You can see it. Anyway, the paper does it. It's complicated. It's not as simple as it should be, in my opinion. But basically, each cycle, the memory controller computes a slowdown value for each thread with a legal request, meaning a request that can be scheduled at this point in time, right? Because if a request cannot be scheduled at this point in time, you don't care. Because there's some resource conflict, you should not take that into account. So you basically compute the slowdown for each thread, memory slowdown, and you compute an unfairness value, meaning the maximum memory slowdown in the system for each thread divided by the minimum memory slowdown in the system for each thread, any thread, basically. And that's the unfairness, basically. Unfairness is really the span of slowdowns, let's say, for threads with legal requests. And now the scheduling policy is, if this unfairness is less than some system software specified alpha parameter, then you use a DRAM throughput oriented scheduling policy and you basically FRF-CFS, first ready, first come, first served. Meaning if unfairness is tolerable, you just do a non-quality of service aware scheduling. If unfairness is not tolerable, based on some parameter determined by system software, then you use a fairness oriented scheduling policy and prioritize a request from the thread that is slowed down the most, basically. And then, of course, this request scheduling is a prioritization order. The next order is row hit first. So you basically try to speed up the thread that has been slowed down the most because you're too unfair for our definition of unfairness. So basically, we add this additional prioritization order, which hopefully makes sense. The goal is to minimize unfairness, basically, or keep it, let's say, close to alpha or less than alpha. That's the idea. Yes.
How can we compute the slowdown? Because on one hand, we need the slowdown, the ST for the workload alone, and the one for the shared workload.
Yeah.
So how can we have, like, for every cycle those values?
Yeah, I mean that's what I described with the excess value, stall time excess, right? You need to calculate that stall time excess. And if you want more detail, it's in the paper. Yeah, the paper, it's not easy, basically. You cannot take into account everything, right? We don't take into account write versus read scheduling, for example. If one workload is much more write intensive, it's causing a lot of entry into this write mode in DRAM. We don't take that into account. So it can always be made much better. But this was good enough for the workload we studied, let's say. And I'll show you an example. Okay, so basically, how does STFM prevent unfairness? Remember this picture where we showed that you have a thread that keeps accessing the row buffer. Now we actually have in the memory controller some slowdown computation logic and also slowdowns of the two threads, and an unfairness value and an alpha value, maximum tolerable unfairness, which is set by the system software to be 1.05 in this case, for example. Now let's take a look at how the memory controller behaves. So, okay, T1, T0, you see the requests. T0 is streaming, T1 is random access. So T0's request gets prioritized because they keep hitting in the row buffer, which means that T1 slowdown increases. So at this point, when the memory controller schedules T0's request, it increments the stall time of T1 because T1 gets delayed, right? Compared to when it's running alone. As a result, this becomes 1.03. Unfairness is 1.03, still tolerable. But next time, the memory controller prioritizes T0 because you keep using the throughput-oriented policy until unfairness becomes intolerable, right? At this point, the slowdown, it gets incremented again, T1 slowdown, because T0 did not slow down at all because memory controller was prioritizing T0, right? As a result, unfairness becomes intolerable at this point, right? When unfairness becomes intolerable, what does the memory controller do? It switches to a fairness-oriented policy. Even though row 0 is open here and there's a request to row 0, it says, oh, I don't have a tolerable fairness. And the thread that has slowed down the most is T1, clearly, you can see the counters. So I'm going to prioritize the request from T1. Now you open row 16, which delays thread 0 compared to when it's running alone, right? Because thread 0 should not have experienced this if it were running alone. It should basically stream through the row buffer clearly. As a result, unfairness goes down and you're still below alpha. So you switch back to throughput-oriented scheduling policy. You keep scheduling requests oldest first in this case, right? So T0 is oldest first, it happens to be. It opens row 0 again. And at this point, kind of both threads slow down because you discovered that your row buffer was not open, etc. Okay, you can do the calculations basically. And maybe your parallelism was also destroyed, etc. Okay, but at some point again, unfairness becomes intolerable. So you switch to the fairness-oriented scheduling policy to keep unfairness in check. So that's how the policy keeps operating, right? It kind of makes sense, hopefully. You keep switching between fairness-oriented and throughput-oriented scheduling policy to keep the unfairness in check. So to be able to do that, you need to calculate slowdowns, obviously. Okay, I'm not going to go more into detail over here, but for example, by configuring alpha, the system software can decide a better trade-off between fairness and performance. And the paper explores that actually. If alpha is too small, it's actually bad for both fairness and performance. If alpha is too large, it's also bad for fairness and performance. You really need to pick an alpha that's somewhere in between. And then if you want to add priorities to different threads, for example, T0 is more important, or T1 is more important for some reason, then what you do is you basically scale the slowdowns. You wait, basically we introduce the notion of thread weights here. You can think of this priorities, but maybe more principled. You weigh the slowdown with the weight of the thread, basically. If a thread that's important has experienced some slowdown, you multiply it by the weight. As a result, that thread seems to have experienced more slowdown because it's higher weight to you, even though it did not. But it's higher priority, so you scale it up. And that's the idea over here. Okay, so if you look at this, there are upsides and downsides of like any algorithm, right? Clearly, this is the first algorithm for multi-core memory, fair multi-core memory scheduling. Provides a mechanism to estimate the memory slowdown of a thread that could be useful if it was accurate. Good at providing fairness, and being fair can improve performance. So you can see the results. I'm going to show you results from a later paper later. But of course, the downsides is, as I will show you, it doesn't handle all types of interference. This will become more clear in the next work, which is interesting, I think. It's complex to implement. Maybe you can remove that somewhat. It's actually pretty complex to implement because this doesn't even take into account all possible sources of interference that are happening in the memory controller, right? Like write to read interference, right? And also the bank-level parallelism a little bit. It's somewhat estimated, basically. Slowdown estimations can be very incorrect. Still, they're correct enough, or they're good enough, let's say. We don't need to be completely correct in the slowdown estimation, right? As long as we can make a good, as long as we can make the right decisions, switch the policy at the right times, so that all applications get good performance, right? So the goal is not to be completely correct in a sense, but there are later works that build on this work to make these slowdown estimations much more correct, much more accurate, let's say. Okay, and that's the paper. You may want to read it. This is a paper that you're going to implement, I think. Well, you have some homework questions about, let's say. Any questions so far? Yes.
Just wonder, does current memory scheduler know the thread information? For example, the first ready, first come, first serve.
Yeah.
So
Yeah, things have improved. So I think new memory schedulers are, yeah, they have some information about threads. But at the time we were writing papers, no. For a long time, they did not have that information, which I think is a bit sad because it's very easy to pass that information. Yeah. Yeah, we had some pushback from industry saying that, oh, how can I communicate thread IDs, like hardware context IDs, to the memory controller? And I never understood that feedback very well. Okay, I can empathize with it, but it's a few wires, right? There are much more difficult things in life than adding some more wires to your communication path. But I mean, again, this is the mindset, right? The mindset is I have this working thing, and whenever a new idea comes up, the first thing is, oh, why should I change, right? If you remember that picture in that book, it's exactly like that. That's how it is. People don't want to change because it's working, and for some reason they're allergic to change. But yes, that was actually one of the pushbacks for this. In any novel idea, there is always pushback, and even a few wires may make a difference. So imagine this, even adding a few wires to communicate thread information within a chip took such a long time. Now we're dealing with processor DRAM interface. Adding wires is much worse, much more difficult over there, right? These are off-chip interconnects now. Imagine the resistance to that idea, right? It's a bit sad to think of it this way, but this is what you deal with in real system designs. Yes?
When you previously said that having too large of an alpha also degrades performance, did you mean as like in comparison to the optimal performance the system could achieve?
Yeah, exactly. Optimal performance the system could achieve, yes.
Because
you keep switching the robot for a lot, right? So if your alpha is too low, then you basically have no slack for exploiting robot for locality in this particular example, for example, right?
And then if it's too high, it just doesn't actually work at all.
Exactly. If it's too high, you never switch between the two different policies, basically. You can think of it the extremes like that, right? If it's too low, you always switch between the throughput-oriented policy and fairness-oriented policy on a cycle-by-cycle basis whenever you're making a decision. If it's too high, you never switch. And both are bad for, actually, both for performance and fairness, actually. Too low alpha actually has the opposite effect. Your fairness is not optimal at alpha equals 1, for example, because you're switching too much. As a result, you're slowing down both threads a lot. Yeah.
So one drawback I see for this proposal is that if you increase the number of threads by a lot, it will be hard to scale because then you have to keep track of all the threads.
That's right. Yeah, yeah. In general, yeah, that's true.
Right. So if you consider deploying this in a scenario where it would be very, very good, which I can see is cloud providers, which really want to make use of their infrastructure to maximize the throughput for the available hardware, right? So how would the design points change when you think about this solution in context of these data centers or let's say cloud systems?
Yeah. Yeah, but that's a very general question. Maybe we can discuss it after we see some more policies because, yeah, the thread state that you need to keep determines how many threads can you keep track of, right, in the end. And if you reduce the thread state, the amount of state that you have for each thread, which is high in this case, but you can reduce it, I think, with the other ideas that we will see. You can accommodate more threads, of course, right, to keep track of in the memory controller. But yes, I think that certainly the cost, the scalability of the idea is how much state you keep for each thread, right? It's determined by that. Okay, so let's move to the next idea. I like this work actually a lot. But basically, while we were doing these studies, we realized something that is very fundamental. So if you design the processors, if you're taking digital design and computer architecture, for example, we discussed out-of-order execution, caches that can generate more requests. We discussed run-it execution a little bit in this course. Basically, processors try to tolerate long latency, long memory latency, by generating multiple outstanding requests to the memory system. That way that you can overlap the latencies of different requests. This is called memory level parallelism, and there are methods for enabling memory level parallelism: out-of-order execution, non-blocking caches, run-ahead execution, prefetching can be considered also. But these are effective only if the DRAM controller actually services the multiple requests in parallel in DRAM banks, and I'm going to show you that. In today's systems, multiple threads share the DRAM controller, and DRAM controllers are not aware of threads' memory level parallelism. Basically, they can service each thread's outstanding requests serially and not in parallel. So basically, all of that effort you make in the course to improve parallelism can be destroyed by a memory controller that doesn't preserve that parallelism. And let me show you this pictorially. So let's say you have two banks, a toy system, a single thread. This single thread computes, it generates two DRAM requests. To be able to make progress, both of those need to be serviced. So these two requests go to the memory controller schedules one to bank 0, the other to bank 1. And while these two requests are being serviced in parallel in the two banks, the core stalls clearly. It's waiting for both requests so that it can make progress. Imagine this, that you have two loads and the result needs to be added, for example, right? Okay, and then one request finishes. You cannot make progress still because you need the other request so that you can do the add. And then the other request finishes and then the core can continue computation. So this is good, clearly. We parallelize these two requests. They go to the different banks. So their latencies are overlapped, right? So bank access latencies or two requests are overlapped. As a result, thread stalls for approximately 1 bank access latency, right? Of course, there are some other latencies in the interconnect, etc. I'm kind of ignoring them over here. Those are these portions, little portions over here. Assume that the bank access latency is the dominant one over here. Okay, now let's take a look at what happens if you have two of these threads executing at the same time. Let's assume that we have a baseline scheduler that's not aware of each thread parallel. Both threads execute, they each get to two DRAM requests, they send their requests, and these requests get ordered in the memory controller that look like in a way that looks like this. The memory controller first takes thread A's request to bank 0, schedules it, and then it takes thread B's request to bank 1, schedules it. Both threads stall clearly. They still didn't get their request yet. And then thread A's request to bank 0 gets done. The memory controller takes thread B's request to bank 0 and schedules it. And then thread B's request to bank 1 gets done. And then the memory controller takes thread A's request to bank 1 and schedules it. So what happened was both threads stalled approximately for 2 bank access latencies because each thread's requests, basically neither thread had its requests to different banks serviced in parallel. Its requests were serialized, right? Okay, the question is, can we do better? And the answer in this paper is you can do better, much better. The idea is you don't need to serialize the requests of both threads. If you're aware of the parallelism of threads, memory level parallelism or bank level parallelism of threads, you could do a much better policy. In this toy example, these are four requests that came to the memory controller. Memory controller first takes thread A's request to bank 0, schedules it. Then it recognizes, oh, there's another request from thread A in my queue to bank 1. Let me take that and schedule it so that I can maximize the parallelism of this thread in the banks. Okay, at some point, the first request is done. So bank 0, the memory controller takes thread B's request to bank 0 and schedules it. And then the second request to bank 1 gets done. The memory controller takes thread B's request to bank 1 and schedules it. Now something nice happened. The thread A got its requests, both of them back, and it can continue its computation. And thread B didn't hurt, meaning its requests still got serviced in parallel, but just later than thread A. As a result, you save cycles on thread A, as you can see, because you serve the thread's request in parallel. So you preserve the parallelism, bank level parallelism of both threads. And as a result, you can reduce the stall time of some threads, not all threads, clearly, right? And that's the idea, basically. build a parallelism-aware scheduler that can achieve this. And the paper, basically, the average stall time became, as opposed to 2 bank access latencies, it became 1.5 bank access latencies if you average across threads, right? Okay, so how do you actually build a schedule like this? And if you look at the paper is a more sophisticated example with row buffers, different rows, etc., more banks. You can look at the paper. So basically, if you want to build a parallelism-aware scheduler, you want to exploit 2 principles. One is called parallelism awareness, bank parallelism awareness. And if you want to exploit bank parallelism for a given thread, schedule the request from a thread to different banks back to back. That's what we did in the previous example, right? We took thread A's request, and then if you want to schedule something to some other bank, prioritize thread A's request. Another bank, prioritize thread A's request so that you can maximize the parallelism of that thread so that they don't get serialized, right? The requests don't get serialized. Clearly, this is good because this preserves each thread's bank level parallelism as much as possible. But if you keep doing this, if you keep prioritizing a thread, you may actually cause starvation. So you need to prevent that starvation, meaning you keep servicing a thread's request, and the thread keeps generating requests. So, and you keep prioritizing thread A this way to different banks, and you may cause starvation to different threads, clearly. Because as you keep servicing requests, the thread can actually be generating more requests, right? Okay, so the second principle to eliminate starvation is called request batching, which is a very old idea, actually. It's used in disks, for example. It was first proposed for disk scheduling. But basically, the idea is to group a fixed number of oldest requests from each thread into what's called a batch. And the service this batch before all other requests. So you create a batch, say, this is the oldest batch. I'm going to service it. I'm going to prioritize the requests in this batch over all of the other requests, right? And you form a new batch when the current one is done. This way, you guarantee some progress from all threads, right? Because you're forming this batch by grouping a fixed number of oldest requests from each thread. Every thread can contribute if there are requests in the memory controller. And it's a fixed number per thread. So it eliminates starvation and provides fairness. It also allows parallelism awareness within a batch. So we will see this, how to do this in more detail. But conceptually, it looks like this. You have threads, you have requests that are queued up in 2 banks. Each thread has 2 requests, let's say in this picture. You form a batch, and you basically start doing parallelism awareness within a batch. Thread 0's request first in parallel. Thread 1's request first, next in parallel. In the meantime, some other requests keep coming, but you don't insert them into the batch because you say, okay, this may cause starvation, right? There could be better methods of handling. And if you read the paper, there are a lot of methods explored, but this batching works fine, at least in that state of the art time. Okay, and thread 0 has more requests, but they don't get included in the batch, as you can see. You need to finish the batch first. And then T2's request in the batch gets prioritized. And then T3's request in the batch get prioritized. And then you form a new batch. Okay? So these are the 2 principles, basically. And you can employ each one of them without the other, clearly. But the paper shows that employing both of them together provides the highest performance and fairness. Okay, let's take a look at these components and how they're implemented. So this hardware cost was an important consideration for us when we actually implemented this. So this is going to be much more simple compared to stall time fair memory scheduling. But batching is very easy, actually. Well, you need to have logic plus storage. Each memory request has a bit that's called a marked bit associated with it. This basically says the request is in the batch, and then every other request is not in the batch, because we just keep track of a single batch in this case. You could potentially extend it to multiple batches. That makes things more complicated. So we wanted to have oldest batch and form a new batch when you're done, kind of approach. So how do you form the batch? You mark, the memory controller marks up to marking cap oldest requests per bank for each thread. So this marking cap, again, could be supplied by the operating system or someone, as we discussed in the paper. And mark requests constitute the batch, and you form a new batch when no mark requests are left, as we discussed. And the prioritization policy is very simple. Marked requests are prioritized over unmarked ones. There's no reordering of requests across batches, so no starvation. And this also helps fairness. It by itself doesn't lead to completely high fairness, but no starvation is a good start, basically. Starvation freedom is a good start. So the question is, how do you prioritize requests within a batch? And that brings us to within batch schedule. Now, this batch is nice because batch gives you starvation freedom. Now you can explore different policies within each batch, right? So you can use any existing DRAM scheduling policy, like we discussed. FRFCFS exploits row buffer locality, but it's unfair. But now its unfairness is very much bounded by your batch size, right? So you can actually use FRFCFS and gain even more performance using batching, as the paper shows. But we also, as we showed, we also want to preserve each thread's bank level parallelism, right? And for that, we need to service each thread's request back to back. So how do we do that? And the way this paper introduces to do it is by having the scheduler compute a ranking across threads. We're going to later deconstruct this ranking. It turns out even this is complex. But at the time we were designing it, it's much less complex than the prior work, let's say. So basically, the scheduler computes a ranking of threads when the batch is formed. And higher ranked threads are prioritized over lower ranked ones. And if you do this ranking and prioritize threads based on the ranking, what you're doing is you're improving the likelihood that requests from a thread are serviced in parallel by different banks, because every bank obeys that ranking, right? If there's a request to bank 0 from thread A, and thread A is ranked highest, then bank 1 is going to obey that ranking also. Bank 2 is going to obey that ranking. Bank 3 is going to obey that ranking. So if thread A has requests to every bank, thread A will be prioritized across all those banks. And then the ranking goes to the next thread in the rank, right? So basically, that's the idea. Different threads are prioritized in the same order across all banks. And we will see an example of this also. The question is, of course, how do you compute this ranking of threads? Now it becomes interesting also. So let me give you the thread ranking at a pictorial view. So you have bank 0, bank 1. You have two different threads, A and B. And the problem was this, basically, what I showed you earlier. It's exactly the same. Each thread request gets serialized. Both threads wait. If you rank thread A higher than thread B, both banks prioritize threads in the same order. As a result, blue thread waits less, right? That's the idea of ranking. And you can generalize it to many banks, generalize it to many threads. It just works. Okay, but ranking scheme itself affects system throughput and fairness. So ideally, we would like to maximize system throughput, core utilization, how much each core makes progress, and minimize unfairness. In this case, the definition of unfairness was to equalize the slowdown of threads, as we discussed previously. But now we're not going to compute slowdowns. We're going to approximate it based on what we have seen. Okay, so if you want to maximize system throughput, you want to minimize the average stall time of threads within the batch. So you're doing all of this within a batch, of course, not globally. Right? Global is a harder problem, of course. So if you want to minimize unfairness, it turns out you have the same goal as maximizing system throughput in this particular case. You want to service threads with inherently low stall time early in the batch. Why? Because delaying memory non-intensive threads results in high slowdown. So let me give you an example. You have a memory intensive thread. In the baseline, it waits for memory for 10 seconds. You have a memory non-intensive thread. In the baseline, it waits for memory 1 second. If you delay both of them by 1 second, which one loses performance more? The memory non-intensive one, right? Because one of them waits for memory for 10 seconds. The other one waits for memory for 1 second. You're introducing a delay of 1 second to both. The one that was waiting for memory for 10 seconds experiences a slowdown by 10%. The one that's waiting for memory for 1 second experiences a slowdown by 100%, right? Because you're doubling its wait time to memory. So basically, this says that you should not delay the memory non-intensive threads, because the impact of that delay is much higher on the non-intensive thread compared to the intensive thread. And this brings us to the shortest stall time first, or shortest job first ranking. There's a theory behind it, and the paper also talks about it. If you want to basically maximize system throughput, you want to have the shortest job first. In this case, job is the stall time of the threads, if you will. But again, I'm not going to talk about it. Clearly, actually, there's a lot of industrial engineering research that talks about how to provide optimal system throughput in factories when you have different latencies in terms of the component production, right? And you want to finish a component. And I would recommend you take a look at this paper that's referenced. It's a very fundamental paper. But basically, it's the same principle. The controller is going to estimate each thread's stall time within a batch. And it's going to rank threads with shorter stall time higher. Because why? Why? Those threads are fundamentally less memory intensive. If you delay them, you're going to get much higher slowdowns compared to delaying threads with longer stall times to begin with, because they're much more memory intensive. And I already gave you the insight with a 10-second versus 1 second inherent delay, right? Okay, so now we're getting into a real controller that can do this with low hardware cost, as we will see. So basically, this is called shortest stall time first ranking. We're going to compute two metrics in the controller. One is the maximum number of mark requests to any bank. This is called the max bank load. This is basically you rank the thread with lower max spent load higher. I'm going to give you an example of this. It's best seen with an example, I think. So this hopefully leads to low stall time. And then we look at basically threads with lower max spent load are fundamentally threads with lower stall time. And then we're going to look at total number of mark requests. This is called total load. This is a tiebreaker, basically. What if two threads have the same max bank load? How do you break the tie? Well, one thread may have actually a much higher total load because it may actually be generating many more requests to other banks. So we actually take that into account also. We rank the thread with lower total load higher. Okay, let's take a look at this example. The paper has a more detailed example, as I said. These are 4 banks, 4 different threads. They're heterogeneous now. Let's compute the max bank load and total load of each thread. So max bank load correlates with, let's say, how long the thread needs to wait to service all of the requests within a batch. So let's take a look at thread 0. So thread 0 has 3 requests, each of them to 1 bank. So its max bank load is 1. The maximum load to any bank is one request, right? Its total load is 3, basically sum up all the request count. Okay, that's easy. T1, its max bank load is 2. So basically it has 2 requests to bank 0. If this thread was running alone on the system, its stall time would be 2, right? That's what max bank load is trying to approximate. But its total load is 4. Thread 2, its max number of requests to any bank is 2, as you can see, to 2 banks. And its total load is 6. And then thread 3 is the slowest, longest stall time thread because it has 5, it is a max bank load of 5 requests. Its total load is 9. So you can calculate this really easily by observing what's going on in your memory request queue, right? And you can design hardware circuit for this, right? Okay. And then the scheduler computes the ranking. T0 is greater than T1, greater than T2, T3, conveniently cooked up, basically. Okay, now let's take a look at what the scheduler does with this, right? So this is the baseline scheduling order, arrival order. Assume that that's the arrival order. I'm ignoring the row buffer here. The paper is an example of the row buffers. It complicates things, of course, no question about that. But this is time. And if you do the arrival order scheduling, let's take a look at how long each thread stalls. Okay, these are the stall times. So if this is your scheduling order, arrival order, I'm going to ignore switching penalties between banks, etc., shared channel. They're all ignored in this case for the sake of example. But T0, let's take a look at how long T0 stalls. Last request of T0 is serviced after 4 time units. So a stall time is 4. Okay, last request of T1 is also serviced after 4 time units. So stall time is 4. Last request of T2 is serviced after 5 time units. So stall time is 5. And last request of T3 is serviced after 7 time units. So stall time is 7. Hopefully this is clear, right? This is assuming that all banks are independent in this case. Of course, there are some additional latencies because there's a shared channel, but we cannot do anything about that, basically, about the shared channel. It's a tax you pay for every request, right? But bank level parallelism, we can do something about, as we will see. Okay. So basically the average, if you compute the average, if all threads are equal, you would compute the average stall time and you get 5 bank access latencies. With parallelism-aware scheduler, you do much better, basically. Basically, our scheduling order would be based on our rank order. So we're going to schedule requests from thread 0 first. So thread 0's requests are going to be serviced in parallel in the 3 banks that they go to. So stall time is going to be 1. After 1 time unit, it's done. Thread 1's requests are going to be scheduled in parallel as much as possible again. So stall time is 2. Thread 2's requests are prioritized next. Stall time is 4. And thread 3 is not going to experience any stall time benefit. You can think of this as kind of like Tetris, right? You form these chunks of Tetris based on the colors. And then you basically maximize the throughput and putting these Tetris pieces together, right? And that's the idea. Basically, the average is much better right now, 3.5 bank access latencies. So just by doing this, in this cooked up example, you improve performance by 30%, right? Of course, this is within batch, right? What happens across batch is we're not analyzing it over here. It can hurt some of this, but it can also be okay, right? I'll show you simulation results that show that it actually provides performance, but not 30%, let's say. Okay, so that's the idea, basically. I think conceptually, hopefully it's interesting. This is basically how you can make a design much more implementable. But it's also a different idea, right? It's not like we're taking stall time fair memory scheduling and making it implementable. We're using some of the insights from there to do the stall time ranking, let's say, But we're also using new insights to actually parallelize requests, for example, in the banks. And this is the final scheduling policy, basically. It's a prioritization order again. Marked requests are prioritized over others. Now we're going to introduce row buffer. Row buffer always complicates the problem, basically. So we basically put that as second order. Row of hit requests are prioritized over others, and then higher ranked threads are prioritized over others, and then oldest first is prioritized over others. Now, based on what I described, this may sound non-intuitive to you because ideally you would have marked requests and then higher ranked thread first, right? And then row buffer may come later. But row buffer locality is actually quite strong, basically. So if you read the paper, you will see that we experimented with different policies, and this policy performs slightly better than the other policy where we reorder 2 and 3, meaning higher ranked threads first. Because row buffer hits versus misses changes the length of these request writes. Now each request takes different time units. That's why it becomes a little bit difficult. So that Tetris becomes much more difficult because now you need to compute the dynamic reordering. And of course, at higher complexity, you can come up with a better solution, but we don't want higher complexity. We want a simple policy. And this is the simple policy that we came up with. Okay, so you can see that this is batching and this parallelism-aware within batch scheduling. Now I should point, there are 3 properties over here. Clearly, this tries to exploit both row buffer locality and intra-thread bank parallelism, 2 and 3 over there. There's no perfect way of combining them yet. It's work conserving, meaning you don't waste bandwidth. If there is a request, if there's a bank, and if there's a request to that bank, you schedule it. It could be marked, it could be unmarked. This is a prioritization order, basically. This doesn't say the batch should be serviced as a whole in the entire memory system. If there's a request that's not marked to a bank that doesn't have a marked request, then you schedule that request, right? So you don't want to waste bandwidth, basically, because wasting bandwidth can actually, even though it's not perfect from some of the analysis that I've shown you, wasting bandwidth actually loses, it's hard to make up later, basically. And marking cap is important. This is basically, again, how many requests get marked and be considered as part of the batch for a given thread. If you have a too small cap, your batches are smaller. As a result, again, your row buffer locality gets destroyed because you have too few requests from a given thread in a batch. If you have too large of a cap, then your batches are larger, which means that you're including requests from very intensive threads inside the batch, and very memory non-intensive threads get less opportunity to be included in the batch. So they have to wait for the batch to be finished so that they can access the bank, basically. So this is a clear trade-off, and the paper analyzes this trade-off also. Whenever you have thresholds like this, you need to analyze the trade-offs, but there's no, let's say, perfect solution. Some people actually considered making this marking cap, for example, dynamic, and there's other work that's built on our work on that. Okay, there are many more trade-offs to analyze. So let's take a look at the hardware cost. Hardware cost is actually quite tractable compared to especially what we discussed, stall time fair memory scheduler. So storage cost is very low. And there are no complex operations like divisions like we had in the stall time fair memory scheduler. It's also not on the critical path. But even this, we're going to deconstruct this, as I said, if you have time. But basically, even this turns out to be not as easy to implement. So you want even simpler scheduling policies going into the future. But I think the fundamental ideas that are in this design are actually quite useful for future systems. In fact, some of the Samsung SoCs used some of the ideas over here, batching and parallelism awareness. They didn't implement the exact same policy, but they used some of the ideas to approximate, let's say, what we did. Okay, let's take a look at the performance of this. I'm not, performance in terms of unfairness and performance as well. I'm not going to go into a lot of detail, but this is FRF-CFS, average across many, many workloads, 4-core, 8-core, 16-core. You can see that it's very unfair. First come, first serve is a bit fair, but its unfairness actually grows with more cores. This is a fair queuing mechanism, network fair queuing applied directly to memory controllers. Again, it doesn't work very well, as you can see, especially the core count increases. Stall time fair memory scheduling actually works reasonably well, as you can see. But parallelism-aware batch scheduling improves over stall time fair memory scheduling even more. So parallelism-aware batch scheduling actually improves fairness better compared to stall time fair memory scheduling. Even though it doesn't directly try to compute slowdowns, but computing the slowdowns is not easy, as we discussed, right? And system performance also improves. You can see that compared to the system performance of the best prior scheduling policy, which is STFM, the system performance is reasonably high, let's say. And there are multiple reasons. One is you're improving fairness, and the second is you're exploiting bank-level parallelism much better. Okay. So let's talk about the pros and cons over here. So this is, again, the first scheduler to address bank-level parallelism distraction across multiple threads. Simple mechanism, well, simpler compared to STFM. Batching provides fairness, and ranking enables parallelism awareness. As I said, these are orthogonal concepts. It could be employed separately also, individually also. The downsides is, I think, latency-sensitive applications have a problem with this, basically. If you're not injecting a lot of requests to the batch, for example, you get delayed behind the batch, regardless of however long the batch is. If the batch is small, it's less of a problem, of course. But you want to have batches that are reasonably large so that you can exploit robo for locality. And if an application is not memory intensive enough, it gets left out of the batch. So it needs to wait for the batch to finish. And this actually hurts the performance of those latency-sensitive applications. They just have one request, but they have to wait for the entire batch to finish. An entire batch may take some time. That's why I think this prompted us to think differently about memory scheduling, and you will see that later on. You really want some heterogeneous policy in the end that can cater for different applications. Different applications have different characteristics, and if your policy can adapt to different characteristics, you can do much better. Yes?
But other policies like first come, first serve, or the robo for hit rates, they don't help these low latency applications either.
That's true, yeah, that's true, yeah. I'm comparing basically to what should happen, let's say. I'm not comparing to other policies. You're right, absolutely. Okay, and maybe there are some other downsides. You could argue that this is still complex, as we will argue in the later works, right? As we push towards simplicity more and more, we will argue that this is actually still complex, basically. It's implementable, but it's complex. Okay, any questions? Yes.
So it seems like the batching mechanism is primarily to promote fairness, whereas the ranking mechanism is mostly to improve performance by doing better Tetris. So I guess the question is, if you just do batching to improve fairness, does that improve the performance over the first option, I guess the baseline option you have?
Yes, absolutely. And it's in the paper, basically. If you just do batching, it's good for performance also because you reduce unfairness in the system, right? You improve core utilization again. Same arguments we had.
And another question, just to understand mechanism, is it basically always doing batches, or is it sort of like batches or interrupts that like sometimes?
It's always doing batches, basically. You always form a batch and you always schedule marked requests. Well, you always prioritize marked requests.
Oh, wait, thank you. Yeah, that makes sense. Just because everything was presented in the context of inner batch. Yeah.
Okay, but you can imagine other, I think there's some room for creativity over here. It's a bit old right now, but if you look at the paper, we examined a lot of different policies. For example, we examined violating the batch a little bit because when you see a request coming from some application, inject it into the batch, for example, if it's a low latency application. It doesn't work perfectly, unfortunately. Yeah. Okay, so, and that's the paper, and you may want to read it. And this is a shorter version of the paper that may be easier to read. Let me give you another idea that tries to solve the problem of latency sensitive applications. I'm not going to talk about this more, a lot actually. I'm just going to give you the basic idea and basic results. It's actually, the goal was to improve throughput in this case. And again, we use a lot of, let's say, scheduling theory to design the scheduler. So there's a lot of depth into this, but we don't have time to cover a lot of depth really. Let me just summarize. So in this case, our goal was to maximize system performance. We said, okay, forget about fairness for a while. How do we deal with even system performance in multi-program context much better than prior work? And the main idea that's developed in this work is to prioritize the thread that has so far attained the least service from the memory controllers. That's why it's called adaptive per thread least attained service scheduling. And if you want to really appreciate the idea, you should read the paper, but we rank the threads based on the attained service in the past time intervals and enforce thread ranking in the memory scheduler during the current interval and prioritize the threads that have attained less service in the past. So why does it work? Basically, it prioritizes memory non-intensive threads. So this attained service is a proxy for, like, let's say, computing the intensity of the threads. So if a thread did not attained service, meaning, okay, how do you define attained service, first of all? Attained service is, it could be defined based on requests. It could be defined based on cycles. Let's define based on cycles. It's basically how many cycles of memory service did this thread get? Meaning how many actual cycles did the memory spend servicing this thread requests? You can have a counter per thread. Each thread has a single counter. And this is the number of cycles the memory spent servicing this thread requests. That's very easy to compute. Very lightweight, actually, if you think about it. And you do it on an interval basis. You don't basically accumulate it forever, these counts. You wait some intervals, and the paper talks about all of that, basically. I'm not going to go into detail. But fundamentally, if a thread did not request much service so far from the memory and attain much service from the memory, this could be due to multiple reasons. One is memory controller did not prioritize it. And the second is, fundamentally, the thread did not generate a lot of requests, right? So this least attained service ranking covers both. If a thread did not generate a lot of requests, it fundamentally didn't attain much service. So maybe it should get prioritized anyways, right? Because it's light. It's not going to delay other applications. And if it at some point changes behavior, it's going to attain more service, and it gets naturally deprioritized over time, right? That's the idea. By keeping track of the attained service from the memory, you have a very smooth policy that adapts to how much the thread is requesting from memory, plus adapts to how much the thread is given. Right? If a thread is given a lot of service in the recent times, it naturally gets deprioritized. If no one is requesting, it keeps still accessing memory. Right? So I like this policy because it's very lightweight. And the reason why it improves performance is it naturally prioritizes memory non-intensive applications that are more likely to keep their cores busy. Because again, these memory non-intensive applications, they once in a while generate requests. This is similar to GCC, for example, as we have seen earlier, right? And if you service them very quickly, they go back to their cores and they do computation, and they're not going to disturb the memory controller for a while. Meaning they're not going to interfere with other applications. And this is a very nice, simple way of prioritizing. And this actually works nicely. You can see that there are experimental studies in the paper across many memory controllers, keeping the number of cores constant. You get significant performance improvements. And the performance improvements improve as you get more bandwidth constraint. I like this figure because this also shows that if your system has a lot of bandwidth, like 16 memory controllers for 24 cores here, I think it was 24 core system, yeah, it says over here, you don't get much performance. All memory scheduling policies look similar. But this is a very expensive system. If you're very cheap in building your system and memory bandwidth is a huge bottleneck, you have 24 cores, only one channel, then you can see that the memory scheduling policies have huge differences, right? Like this is FCFS, for example, and there's maybe, I don't know, 5x difference between FCFS and Atlas over here. And Atlas actually buys a lot more performance. This is a performance improvement compared to the best prior scheduling policy, I think. Yeah. Okay. And best prior scheduling policy is different, I think, compared to in different kind of systems. Right? Here it's STFM. Here it happens to be PAR-BS. I think everything else is PAR-BS. Just this here it's STFM. Okay. And then there's the other study where you keep where you vary the number of cores while keeping the memory controllers at 4. And in this case, again, a very similar observation exists, right? This is across many applications. Again, performance benefit increases as your bandwidth, memory bandwidth, becomes more constrained. Here you have, I think, 4 memory controllers on 4 cores. So you have ample bandwidth. So you don't gain as much performance. But here you have 32 cores on 4 memory controllers, which is not unreasonable. And you have 11-point performance improvement compared to PAR-BS. Okay. So let's talk about Atlas. Even though I didn't go into a lot of detail, hopefully you get the idea. It's good at improving overall throughput. Fairness was not a constraint here, for us at least. So compute-intensive threads are prioritized. It's low complexity. It's actually the lowest complexity scheduler that we talked about so far. Well, ignoring FCFS and FCFS clearly. FCFS is not scheduling anyway, right? First come, first serve. You don't do any reordering. So it is scheduling at some, but it's not reordering, let's say. And there's something we did not talk about. What happens if you have multiple memory controllers? You need to coordinate between them if you want to maximize performance. And in this case, coordination happens infrequently. But I'm not going to go into that in detail since we don't have time. But the downside is now you have fairness problems, basically. lowest or medium ranked threads get delayed significantly, so you have high unfairness, but that was not our design goal, but it needs to be solved. And we're going to talk about that next. And if you're interested, you can take a look at this paper. I like this paper a lot because actually it's inspired by something that I didn't even talk about, like why does this make sense from a scheduling theory perspective? But again, we don't have time, so I'm not going to cover this. Any questions? Yes, please.
So in the paper, these intervals in like after which the memory controllers communicate with the meta controller are called quantums, I think. And I'm not sure, according to your explanations now, do the memory controllers locally update their ranking within a quantum or only at the end of the quantum?
Oh, I see. So in Atlas case, we look at multiple different policies. Yeah, in some cases, they update the ranking basically at the end of a quantum. Yeah, in the paper. So you read the paper. Say it again. I can hear.
It was in the lab, so we basically.
Oh, okay. That's right. That's right. Exactly. Yeah. Yeah. Exactly. It was in the lab. So now we're covering it. Yeah. Okay. Let me talk about thread cluster memory scheduling. This is one of the reasons why this is not in the lab. Is this is not. This is harder to build. Basically, we gave you the simplest policy, but we didn't give you Bliss, right? I think that was an extra credit assignment. Okay, Bliss was part of the assignment. Okay, okay, that's good. That was easier to implement, right? Yeah, exactly. So now you know exactly. So hopefully we'll get to Bliss, but we may not get to Bliss, but hopefully you know the basic ideas. Well, let's talk about thread cluster memory scheduling, because this is one of the reasons why we don't give you these in the lab, because they're more expensive, but they buy some benefits, as we will see. Let's take a look at, okay. And then we basically decide to say, okay, let's take a look at the policy space of scheduling algorithms. So we have better system throughput, better fairness. We have, these are experimental study, many workloads, as you can see. 24 core, 4 memory controller system with 96 workloads. So ideally you would like to be here, right? So fairness now I'm defining as maximum slowdown. So you can always improve your definition of fairness. And in this case, we say, if you can reduce the maximum slowdown, you're more fair, basically. And that is true, actually. This is a fairness metric that takes into account performance a little bit also. And there's some theory behind it also that I don't have time to go into. But the maximum slowdown by divide by minimum slowdown is something called max min fairness. In this case, reducing the maximum slowdown improves your fairness, and that's called a max fairness, let's say max slowdown type of fairness. And in our studies, we found out that this is a better definition so that you can optimize for the performance and fairness at the same time. Okay, but if you look at Atlas, it has a system throughput bias, obviously, because it's not designed for fairness at all. PARBS has a fairness bias. So it's more fair, but it's not as high performance. And some other algorithms are kind of obsolete in the space, averaged across many workloads. They may do good individually for some workloads, but on average, you would not choose them, let's say, if you were making your decisions based on average, right? Because this is your Pareto front, right, if you will. These two algorithms make sense to choose. Any other algorithm, according to just these two metrics, is essentially not in the something that you would not choose if you were making a logical decision based on just these two metrics, right? So basically, no previous memory scheduling algorithm provides both the best fairness and system throughput. But our goal was to do both. And the realization in this work is that you need to have different policies to optimize for both. So throughput by its approach ranks the threads based on their memory intensity and prioritize the memory intensive threads, less memory intensive threads. That's the approach, right? So this is good for throughput, this is bad for fairness. I call these the mice and elephants, right? Elephants are the big threads, mice are the small threads. Essentially, elephants are, let's say, killing each other here. Some elephants, like the big elephants, are deprioritized for a long time over here if you do this sort of ranking. Whereas mice are prioritized, so that's good. Mice can run fast now. So fairness biased approach, each thread takes turns accessing memory. So this is one definition of fairness, but you can abstract it away like this. So this is good because now the elephant doesn't starve, but this is bad because it takes a long time to get to the mice, right? Whereas mice, once it has a request, it will not generate a request for a long time, so it basically waits. So single policy for all threads is basically insufficient. This is just an example showing that. So how do you achieve the best of both worlds? And this is the idea basically. For throughput, we would like to prioritize memory non-intensive threads. For fairness, we recognize that unfairness is really caused by memory intensive threads being prioritized over each other. The problem is not the mice. The problem is elephants hurting each other. If you prioritize one elephant over another for a really long time, the big elephant will starve basically, because maybe the slightly smaller elephant will take all the time, right? A long time. Whereas the mice do not consume a lot of memory bandwidth, so they don't delay the other threads as much. So this realization leads to a different policy over here. So you shuffle the thread ranking between the elephants, big threads basically that have a lot of requests. And then these have different vulnerability to interference. As a result, you shuffle asymmetrically. You don't do it symmetrically, but you prioritize the threads that are more vulnerable basically to interference. And the paper has more detail if you're interested. And that's the idea basically. This is the conceptual view. And then the question is, how do you get it down implementable, right? So thread cluster memory scheduling automatically groups threads into 2 clusters. Basically, these are all the hardware context threads in the system. Some of them are intensive, some of them are non-intensive. So you have 2 clusters. You prioritize a non-intensive cluster for throughput, and then you employ different policies for each cluster. As I said, inside this, what policy you employ actually doesn't matter as much, but still we do employ the thread ranking based on intensity. Here we do thread shuffling of threads to form the ranking. Okay, so clustering happens in some way. I'm going to go through this relatively quickly, but basically, how do you identify the less intensive threads? During a time interval, you compute the total memory bandwidth usage of all threads. And basically, you designate the threads that are using a fraction of that memory bandwidth as non-intensive. And that fraction is alpha. It's statically determined threshold. It's 10%, I think, in the paper, for example. And that change, by changing that, you actually change the characteristics of the performance and fairness characteristics of your policy. Okay, so this is one way of clustering, clearly. Okay, you can form more clusters also, but we didn't want to complicate the policy unnecessarily, right? We had intensive and non-intensive. And then between clusters, as I said, we prioritize non-intensive cluster. We discussed this already. It increases system throughput, doesn't degrade fairness. Okay, that's good. Non-intensive cluster, within the non-intensive cluster, we prioritize threads according to misses per kilo instruction, basically the ones that are accessing the memory less. You could also use Attained service, etc. We did not go into those here. But basically, least intensive thread has the greatest potential for making progress in the processor. But again, these are less intensive threads, so it doesn't matter as much what you do, unless your clustering is not perfect, which is the case in real life. Okay, and then the intensive cluster is basically what we are really careful about, because if you do something wrong over here, you delay some thread for a really long time. So basically shuffle the ranking of thread. There are intervals, short intervals, where threads get shuffled, basically. And doing that shuffling, increasing fairness. But treating all threads equally is not good enough, because threads have different characteristics, as you know already. Giving equal turns doesn't lead to same slowdown, let's say. So let's take a look at 2 threads, random access streaming. You know the characteristics of these threads. Which ones slow down more easily? Anybody? Random access. I would argue yes. And this is basically a real study that shows us. If you prioritize random access, you get 7x slowdown for streaming. If you prioritize streaming, you get 11x slowdown for random access. Why? Because streaming can overlap accesses, basically. Okay, let's take a look at this example. Basically, this is memory rows. You have random access thread. It basically, okay, maybe I didn't explain it very well. Let's take a look at it when you will see what I mean by overlap accesses over here. That didn't come out correctly, let's say. So yeah, basically random access thread has a lot of bank level parallelism. That's good, maybe. High bank level parallelism, all requests are parallel. Streaming thread keeps essentially accessing the same bank. Okay, this is going very slowly, but it's actually very fast. So it has high roboffer locality. So when you run them together, this is what happens to the random access thread. Its bank level parallelism gets destroyed, and this request gets delayed significantly behind the streaming request. Now, if you do the opposite, streaming thread doesn't get delayed as much by a random thread, because random access thread fundamentally doesn't have as many requests to a bank, right? Because randomly spreading its requests across banks. That's the idea, basically. That's intuition. So that's why this random access thread gets stuck behind streaming threads that basically, let's say, target a bank. So this thread, the random access thread, actually has much more vulnerability to interference, and this paper actually takes that into account in its shuffling. What it does, it basically quantifies the difference between threads. Bank level parallelism, threads with high bank level parallelism have more vulnerability to interference. Threads with higher buffer locality usually cause interference, and There's a niceness metric computed in the paper, which I think is a very good direction, actually. How do you compute niceness of a thread based on its inherent characteristics? Okay, and then there's a quantum-based operation. During one quantum, you monitor thread behavior, you compute memory intensity, bank load, plasma memory overflow for locality. At the beginning of the quantum, you perform clustering and compute niceness. And you have shuffling interval, smaller intervals where you shuffle the thread ranking in the high memory intensity cluster, so that no thread can destroy the performance, or can be ranked high for the entire quantum, or for entire chunks of the quantum. Okay, I'm almost done. Okay, I think we're almost done. Maybe we'll continue with this in the next lecture. But let me give you the performance results. So this is, I think, important to see. So this is where you will get, basically. You will get to a point that basically breaks this Pareto front, as you can see. Okay, any questions? Yes, please.
Isn't
Say it again.
is it
like operating systems, you say? No. I mean, it's there are similarities. There are certainly some similarities, and I think you appreciate that similarities in operating systems. But this exact policy is not used in operating systems. But operating systems also try to distinguish between the characteristics of different threads, like latency sensitive, meaning user interactive. They call it usually interactive threads. But the way they classify threads is different. They usually say, okay, this is interacting with the user, so I'm going to prioritize it, as opposed to the definition that we have over here in terms of memory intensity. But there are similarities for sure, grouping threads, for example, right? Okay, any other questions? Okay, so then we're done for today. Tomorrow we will pick up from here, and we'll see how much progress we make in the memory controllers, but probably we will continue with emerging memory technologies. Okay, take care.